Mhm. Gīs vai dzirdi? Nu, tomēr neredzu laivu. Tā, gīs vai dzirdi? Pagaid, varbūt tā labāk, vai dzirdi? Halo, vai dzirdi? Jā, labi, lūdzu, atnākšu pie tevis. Tā, tagad es dzirdu, ka tu tur runā YouTube, bet nu, telefonā tas sanāk, es sevi nedzirdu, bet dzirdu tevi. Tā, paskaties, lai translēt to Zoom skaņu. Nu, bet es dzirdu, ka tu tur runā YouTube, bet nu, telefonā tas sanāk, es sevi nedzirdu, bet dzirdu tevi. O, tad tagad viss aizgāja tur arī.
हम्म। Recording in progress.
Hello, colleagues. Hope you hear me, and nice to see you connected. And we will start our workshop in a couple minutes. So, Yanis Kalinskis, nice to see you, and hope you hear me perfectly.
Yes, nice to see.
Okay, good. So, we will wait a couple minutes, and I will start my presentation. But before, I will give some announcements, and we go through our agenda and why we are here, and what we are willing to achieve by these 2 days. Yes, so welcome in Ventspils, who managed to arrive in person, and welcome all online participants as well who are connected now and connecting in the next minutes. So we will start our first MarTe project technical workshop, and this is focused on physical modeling and blue and green transitions. And intention is to show how we can, researchers in this case, model our world in physics and bring this to some kind of products in the future. Today we have day one, and we have following agenda. So first talk will be by myself about physical modeling, some kind of introduction, why we are here. And next talk will be by Modis Dogalis from Riga Technical University, insights of SolidWorks and how it works. And later we continue with more dedicated SolidWorks for future activities and some recent innovations in this SolidWorks software. And it will be joint talk by Martin Johansson and Alex Askidel. After that, we have lunchtime, and actually I don't make a wrong copy of this presentation, so I need to switch to original one. Yes, so this is last copy. Later we will have Christian Tabri, our colleague from Tallinn University of Technology, with his talk about the two tools and numerical access for maritime accidents. And we have two on-place colleagues, Norman Jacobsons and Sabine Opner, which again focusing on modeling using OpenFOAM, and continue with Marina Konyukhova about
megawatts to our area of our hydrogen body. This is Tauron 20 megawatt and Promet Plus 20 megawatts facility. But in terms of production of everything in Poland, this is quite different to your cases in Finland, because we have to calculate in our projects our renewable source.
Yes, so it works. Yeah, and later this day we will have hands-on activities again. So it's some kind of challenging task to try to show how SolidWorks will work in practice. And we will have some kind of hands-on activities to run and see how physical models could be executed. And for next day, we continue with face-to-face talks, and we have, let's say, our keynote from Latvijas Flote, Laura Poga, with her vision about fleet developments and port developments from Riga side, and several talks about modeling, and I will continue tomorrow and describe it in more details. And for today, for hands-on activities, who are willing to participate and join this session at 3 o'clock, 3:30, please respond to my email in the morning, because we need to make it interactive, and we need to know how you contact you and connect you to our workstations. Yeah, so I think this is all from announcements. And if you need internet, you can use Ventspils. I think it should work here, and there should be no problem. And I will continue with my talk. About physical modeling, and trying to summarize what we are doing here. And first, several words about MarTe project and why we are trying to collect all people together here. So MarTe is a maritime technology excellence hub in sustainable blue economy in the Baltics. So it's a project, but we would like to make it sustainable and make after the project community which works together. And our mission is connect science and innovations and support the improvements of a maritime environment, the efficient use of resources, and the development of sustainable blue economy. And this includes everything related to Baltic Sea, coastal regions, ports, and industry who working on these fields, and people who live here, also local authorities and institutes and universities who are trying to do some research and innovations in this field. Project started in 2025, and we're going to organize at least 3 similar workshops for scientific dissemination and show how we can do science and how science could be useful for our industry partners. And in this case, 1 second. Yeah. So MarTe it unite a so-called quantitative innovation helix framework, which collects academia, industry, government, civil society, and environment itself as a wide partner. And this is 2 countries, so Latvia and Estonia. Together we are 13 partners, civil society like a Baltic Coast, Worldwide Fund for Nature, Estonian Iceland Cooperation Council, public authorities like Environmental Investment Center of Estonia, Saaremaa Development Center, Kūrma Planning Region, and Latvian Investment and Development Agency, and supporting with research from Tallinn University of Technology, University of Tartu, Latvian Institute of Aquatic Ecology, and Ventspils University of Applied Sciences. So we are here, and industry and business partners and stakeholders as well, Estonian Maritime Industry Association and Ventspils Freeport Authority. And so how we can combine all together, and how we can boost research groups to communicate with industry and understand what industry partners need, and how research could help to make a new deep tech products in this case. And probably in this day we speak a lot about technologies, but it's good to understand what is technology itself and how it could be developed, and basic principles of technology readiness level. You can see it here. I try to make it laser pointer as well. So we need some ideas, and when we have idea, first of all, we need to define it and make some first assumptions, and we could achieve basic principles observed, so some preliminary studies, feasibility studies, and we got L1. Going next, we need to test this idea. Is this working or not, or it's maybe completely impossible to do something? And we formulate technology concepts and make some first laboratory tests and some first models, maybe on paper, maybe on computer, maybe sitting in laboratory technical benches. And when we are finish our research or make a like an experimental proof of concept, we somewhere in research level 3, and this is mostly institutes and universities do this like research proof of concepts. Next, we need to go and collaborate with industry and think how our ideal concepts could work in real world. And we need to make some kind of prototypes and test them in laboratory, and after that validate in real environment. And usually here, so it's mostly researchers, but here we bring also entrepreneurs and industry who would like to use this technology in later stages. Next, when we are ready to say something, okay, we have a prototype is working as we expected, we need to make it some kind of, not product itself, but a prototype which operational in demonstrated in an operational environment in real life in this case. And after that, we can make our certifications and acquire licenses, for example, if we need to move it to market. And this part is mostly related to industry. In this case, industry need to join this research and bring this efforts to bring this at product level. And if you divide, make a TRL9 and achieve a fully operational system, so we say, okay, our, for example, hydrogen compression system working as we expected, we can sell it. And this goes to fully industry and entrepreneurs who need to disseminate it for later public. And when we're speaking about physical modeling, we are somewhere here, TRL2, TRL6. In different levels, we need different kind of approaches and models. And maybe, first of all, I will say a couple words about Ventspils itself. So we are in Ventspils University, and in university, science related institute is Ventspils International Radio Center, do astronomical, radio astronomical modeling, and far beyond a lot of activities related to space and physics itself. And here is example of some models and real results. I show our telescope, 32-meter telescope, which located near Ventspils in Urbane, 30 kilometers outside. And when we start to develop some new instrumentation or new ideas, so we need, and usually we start with visualizing concepts, and it helps to do some 3D modeling tools. We can use these 3D modeling tools and print a prototype in 3D printers, and these give us like a first preliminary understanding what we would like to create. Later, in later stage, we need to add physics and analyze how physics by simulations involved in this our design. For example, here you see this is like a vertex room of telescope. Here is one more, and inside is a cryogenic system which works in 20 kelvins, so it's minus 250 kelvins. So very dedicated system which have to work on moving conditions. So its telescope is rotating quite fast, and we need to analyze how this model not only smooth design and smooth visual concept, but how it physically operates. And next, we need like a engineers and industry support to create this in a like a physical in metal. And using models, we can skip several steps of like a laboratory testing, trying to understand so how our model will survive under different conditions. And here, how it looks in practice, for example. So we have nice plot, which could be done rather easily, but could be not enough to understand if these, for example, transitions in heat sinks works under cryogenic conditions. So, and first of all, we need to make it drawings. After that, we need to test it, and after that, we can do it in metal and test it in laboratory in metal. And after that, proofing our physical model. And very often this is interactive process. So we're creating a prototype, find out what our model was not precise, and we need to adjust it. Like I mean, physical model of our vision. We adjust model, improve it, and give new results, and we'll see new prototype in a metal. And physics itself. So how we can, what we can calculate using our models, and usually it's starting from structural mechanical, like a stress, strain, deformations, and fatigue and vibrations, which give us some estimate of our constructions. Next, very often we need to include heat transfer, like a conduction, convention, radiation, and thermal management, showing how our, let's say, engine or compression system heats in time. And this is sometimes very critical if you are not able to make an equipment which cooling down in particular temperatures, you probably will be overheated and system not working. Next, we're adding some fluid flows like gases and liquids, one or two or both. And very often we need to make like airflow simulations for water currents, for turbulence and pressure losses. For example, if you're trying to build a wind turbine, so we need to make a analysis how this wind turbine will survive under different wind conditions. And one option, we can use wind tunnels, like a physical wind tunnels, which are good enough to test like a scaled models, but sometimes it's not completely enough to make proper understanding of 200-meter long blade, how it evaluates in different wind conditions. And we definitely need a model of this turbine in our SolidWorks or OpenFOAM, for example, and understand how models could be adjusted with real conditions. Often, and we also use electromagnetic process like magnetic fields and forces and inductions and electrical forces, how they could be modeled. And here's an example of permanent magnet modeling again. So we need to understand how these forces influence of our strengths of our construction and works together with like movements and so on. And next step, we use multi-physics interactions. So we use several like a physical things like a flow and heat, electromagnetic process and mechanics like a structure and thermal coupling. We need to model them and understand how our future best prototype will survive on different conditions. And in many cases, this is not a static process, but this is dynamic. So we need to find out transients and instabilities in our prototype and different conditions, and how in real operation conditions it works. Next step, it could be when equipment is created, or let's say wind turbine is built, we would like to see how long it survives. And it could be so that we create a so-called digital twin, which lives same life as a real wind turbine, but in a digital form, and we can see how these structural changes in time, and if we see some kind of parts of this wind turbine need to be replaced in year time, we already know what we need to buy additional parts, for example. And some example of flow, that's like a compressor chamber, what we are trying to model, and in some kind of dynamical process of liquid and flow and air animation in one compression chamber, for example, and what we can see here, and some kind of different ways and different structures. So before I build a real thing, we can try different scenarios, find out best one, and like save time for prototyping and understanding of things. Yeah, so it's some kind of nice plot that could give us statistics and answers how this equipment works in real conditions. But now we're speaking about like a small scale instruments or models or prototypes, let's say laboratory testing. But very important about extend our physical modeling to air systems, to model a global process which occurs around us. And tomorrow you will see our colleagues from University of Latvia describing how we can also model atmospheric conditions and how this process works. And usually, so it's again, it's like a atmosphere, like a wind pressure, temperature, clouds, extreme weather predictions, ocean models, which involve currents, waves, sea level, and temperature distributions. And actually, each of us use these models almost every day. So probably first in the morning, what are you doing? You're looking on phone and looking forecast for today. Is it cold? Is it raining or not? But behind this is a very complicated atmospheric and air models, which provides us forecasting data. And usually these models are extremely heavy for calculations, so it's not possible to just run it on single station. You need very dedicated clusters for it. And here, these models also give us like a short-term forecasting, let's say couple days, week, couple weeks, maybe month. We're looking also for long-term simulations, saying years and even hundreds of years, showing how our, for example, Baltic Sea change in temperature and saltness level, for example, and how our life changes during this period, for example. And this is, again, physical model, which not only complicated, but also could be not very precise. So, and probably you see forecasts for a couple months, and usually it's 50-50. It could be true, it could be false. And unfortunately, even our technologies at this moment not able to predict what will be after a couple months in our climate. So how it's, is it summer will be warm or it will be raining? Nobody tells you. And this is some kind of variability, but not exactly precise. And for these models, usually we need high performance computing and parallel calculations. And going next, some examples of these models, which so models of oceans and atmosphere, actually a lot of and different one. Here's maybe some of latest one, Copernicus Interactive Climate Atlas, and just showing how temperature rises in exactly northern pole. So we are suffering from higher temperatures actually in last 10 years and it goes 10 years in future. So it's climate changes, and we can see it and we can model how precisely. It's a good question, but it's a tool what we can use. And the same instrument, for example, new European Wind Atlas, which shows how wind resource could be available in a Baltic region. And here is yellow, so it's very windy and very nice for wind turbines. Bluish, it's more or less okay, but maybe not so good. And again, for this model, it takes like 30 years of modeling data. So it's models from 1985 up to 2020 somewhere. So it's modeled data, so about wind resource in complete Europe. And in size, it's around 80 petabytes of data. So if you just compare your hard drives and your computer is around, let's say, terabyte, 10 terabytes nowadays, here is 1,000 times bigger data space what we need and to store and analyze this data. And again, so scientists not only stopping on here, and maybe I will show you some video at the end of my talk. So how looks to model galaxy in millions of years. So it's a forming galaxy, and we could model not only small processes in year, but it's possible to organize and model billions of years of evolution and in distance of hundreds of parsecs. And this quite nice physical model. So again, completely different one. So we're starting from small prototypes and small physical models that we can use and to create like a, let's say, drone or vehicle. But with something completely different. So it's physics, which shows how galactic is formed. And yeah, so it's some kind of nice examples. Yeah, I think I will stop here because it's like a mostly introductory of what you will hear and see in next days. So we cover a long list of different and difficult topics of modeling effects of physics, what we can put in numbers in computer and work with them and see how it evaluates in the product. Yeah, so thanks, and maybe we have a couple questions, time for questions. We'll change to participant view. So I see no in the chat, no questions, so don't hesitate to ask something and to use your microphones as well. So no. In this case, I would stop myself and stop sharing my screen and give floor to Modris Dobelis. Modris, are you here? So I stop sharing screen so you can try to share your screen and continue your presentation about SolidWorks at RTU from academic training to industry certification. And we can start going in more details about modeling things.
Hello.
We see you. We see your screen. Nice birds.
Now you should see my presentation, right? Oh, sorry.
Now we see presentation. Yes. So, if no questions, please.
Is it okay?
Yes, perfect. We see everything very nicely.
Okay. Good morning, everyone. Thank you, Ladislaus, for inviting me to your workshop. I'm honored to be here and pleased to share my academic and research experience with you. My talk is much more down to earth, focusing on introductory education in modeling and simulation. SolidWorks plays a central role in modern engineering education, not only as CAD system, but as a platform for developing engineering thinking. At RTU, the focus is on using SolidWorks to connect spatial reasoning, modeling, drawing, production, simulation, and decision-making, preparing students for real industrial workflows. This presentation outlines how academic training can be efficiently aligned with industry expectations and certification pathways. When we talk about SolidWorks in education, it is important to move beyond the idea of teaching a software tool. In modern engineering programs, SolidWorks serves as a foundation for developing engineering thinking, not just creating geometry. SolidWorks, serious enough for engineering, friendly enough for Latvian education budget. How to forward? Oh, got lost control of. Next slide. Okay. Current engineering SolidWorks performs like BIM, using a single shared model for real-time cooperation, coordinated updates and conflict detection, what engineers generally call PLM, product lifecycle management. Concurrent the widespread adoption of practical application of PLM and BIM models across engineering disciplines will only streamline design and collaboration, but will also fundamentally shape how products are developed, managed, and brought to market, ultimately defining the future of industry. At RTU, we use SolidWorks to introduce students to the cause and effect relationship between design decisions and real-world performance. Every modeling choice, dimensions, constraints, symmetry, or simplifications has consequences later in analysis, manufacturing, or operation. Another key reason for using SolidWorks is continuity. The same model created in a basic CAD course can later be reused for structural analysis, flow simulation, and parametric studies. This allows students to understand that engineering is not a sequence of isolated subjects, but a connected workflow where modeling, simulation, and validation are tightly linked. Finally, SolidWorks is widely used in local industry, which makes it an effective bridge between academic and real engineering practice. Students not only learning concepts, they are learning them in an environment they are likely to encounter again in their professional careers. After explaining why SolidWorks is important, the next question is how it is actually applied in the curriculum. Here I show my flowchart of two of my courses where SolidWorks is introduced early, one of which was enhanced with European funding. I expect it to be reinforced across multiple study courses and levels, rather than being confined to a single standalone course. The introductory overview course is offered to about 200 students each year across 6 study programs. Students first encounter fundamentals of engineering graphics and the basics of SolidWorks. In the advanced course, the focus is on parametric part modeling, assemblies, and documentation. Advanced SolidWorks I deliver to 60 students, and this course follows detailed prerequisite course on engineering graphics. And here students, along with SolidWorks, progress to learn assembly, structure, and design intent, proper use of mates and constraints, and engineering drawing that follows standards and manufacturing logic. A key transition happens when students move from simply creating geometry to understanding why a model is built in a certain way. Here emphasis is placed on model robustness, clear feature structure, and future use of the model for simulation and modification. This approach intentionally prepares students for later courses where the same SolidWorks models are not rebuilt from scratch, but extended into analysis and simulation tasks. In this way, SolidWorks becomes a continuous learning platform rather than one-time software skill. I use the following teaching method. Practical exercises are conducted simultaneously in 2 computer labs of 30 seats each, as RTU does not have a single lab with 80 to 100 seats, unlike a friend of mine, a professor in Germany. I present short theoretical concepts in PowerPoint, stream them to the second lab via Zoom, and record them for later review. Both labs have 2 large screens, and in the second lab, a colleague assists me. I use flipped classroom approach. The students are required to watch instructional videos before the session and then work independently in class and on exercises. I manage the computers on both labs using Day1 software and taking control whenever a student encounters a problem to demonstrate the solution. Usually, if one has the question, several others do too. Then I take the control of the student's screen and share it on both classes, demonstrating the solution without wasting time to walk to the student's seat. Something is wrong with so here is the class I showed before, and somehow the synchronization doesn't work well for me. Sorry. Final goal for the task they have to master is to prove the control over the design intent. In the first easiest step, students are are given typically 4 answers, and they have to choose from the 4 answers the correct one. Those who are not patient may submit the solution, but they just get partial credit. For the serious studies, they need to work constantly on this problem in several steps to solve the problem by themselves. The goal is to let the students practice to master design intent by themselves. And Moodle quiz serves purely for self-assessment. The teacher is built into this Moodle system. At RTU, SolidWorks is primarily used for learning and concept understanding. Models are simplified, assumptions are discussed, and results demonstrate just basic principles. In industry, models are more complex and must be robust, reusable, and clearly documented to support simulation, manufacturing, and decision-making. Historically, industry representatives have sometimes complained about our graduates that they have poor skills in interpreting mechanical engineering drawings. Partially, it was caused by decades of limited funding for PCs and CAD software, as well as university curriculum changes after Latvia regained independence. 10 years ago, we still held so-called CAD Olympic contests for the students to challenge them to more industry-like tasks. But today, such contests are too complex to run them at all. Highlighting these differences in studies helps students bridge the gap between education and real industrial workflows. To extend the impact beyond the university, the current course is being duplicated on an open MOOC platform. Its purpose is to lower the entry barrier, spark interest, and guide motivated learners toward more advanced lifelong learning programs. At the university, they have to subscribe for these later. In recent years, RTU has organized free introductory courses with several EuroCC project initiatives. These courses are not only focused on CAD skills, but also on motivating engineers from the industry and students to use HPC resources for large-scale simulation tasks. Some industry-inspired examples from these activities I will demonstrate in my lecture tomorrow. One practical way to align academic training with industry expectations is through SolidWorks certification. Certifications like CSWA and CSWP and simulations focused exams provide a clear, externally validated benchmark of skills. There is a list of 14 different exams available to RTU students thanks to the current license subscription. In this sense, certification becomes not just a personal achievement, but a bridge between open education, university studies, and industry needs. The illustrated certification track shows the recommended sequence on how to form a clear skills development pathway. For students, certification structures learning, builds confidence, and creates a recognizable reference for employees. In our course, certification is positioned not as an obligation, but as an opportunity. At the end of the course, students may take the certification exam free of charge, and this serves as a carrot rather than stick, which significantly improves motivation and engagement in compulsory university course. From education perspective, certification also benefits instructors by providing a clear target competence level, objective feedback on learning outcomes, and a shared language when discussing skills with industry partners. A straightforward practical approach to parametric feature-based modeling. I was surprised that industry representatives who already work with SolidWorks daily are still willing to take the time to prepare for CSWA certification exam. Here you can see the schedule of these courses which they took after their working hours and took this certification exam when they joined lifelong learning course at the university. To conclude, I would like to return to the main message of this presentation. SolidWorks becomes truly valuable in engineering education when it is used not only to create geometry, but to support reasoning, analysis, and decision-making. By integrating modeling, simulation, and certification into the curriculum, we can better prepare students for real industrial workflows. From an educational perspective, the key is consistency. Consistent tools, consistent methodology, and consistent expectations aligned with industry practice. Thank you, and I look forward for continuing this discussion tomorrow from more technical, hands-on perspective. Sorry for technical problems while switching these slides. There was some problem with my Zoom.
Thanks a lot. We are very appreciate your talk, and this is again what we need for understanding for beginning of work for next talks. And maybe some questions, and just to be sure I understand correctly. In Riga Technical University, you have a main course for students, and also this course is available for not students as well. Is it right?
That's correct. Yes, they are organized some within other projects, some courses, shorter course and extended course like you saw before, 16 weeks or just 4 days. And most important is that these courses are free of charge.
Even for not students. So
yes, anyone that's correct. That's correct, but they usually are organized just once a year. Mm-hmm. For interest from industry.
Mm-hmm. And you show a lot of industry representatives also willing to join these courses even at evening times after work. Could you
yes, that's correct. That was my surprise. I was wondering, they already have work. They work with SolidWorks. And my question was, why do you need this certification? I understood that students need this certification when they are looking for their next job, so they can show that they have some practical skills. But those who are already working, that was my surprise.
Entrepreneurs who are hiring people, are they appreciate these certificates? So they're asking about certificates for people who are looking for work. So how important for like a potential worker or engineer to have this certificate? So how it helps to rise salary or find a job?
Yeah, that's an interesting question to work on this. I have not studied about this. Sorry.
Oh, okay, thanks a lot. Thanks again. And if any would like to ask questions, I see no raised hands and nothing in the chat. Yes, thanks a lot, and we'll see you tomorrow. So I give floor to Martin Johansson. I think he have to be connected. Martin, are you here?
Yes, I am here.
Nice to see you and welcome in our forum.
Thank you.
So, Modis, could you switch sharing of your screen? Okay, yes. So,
And
Martin,
I can also see that Alex is here as well.
I am. Hello, everyone.
Good to see you, both of you. So, Martin, you will start, right?
Yeah, absolutely. And I'm waiting for Alex to start sharing the presentation we have created for this session. But I can just start by saying thank you for having us to mark the first technical workshop. We are, of course, sad that we cannot be on site this year, but we are very happy that you have invited us. And the meaning of our session here is to talk a little bit about the newest features in SolidWorks. And of course, something is from 26 and some are from older versions, but that will be covered by Alex. And I think that I will start by introduce the company we're working for, PLM Group, to start with. So Alex, if you...
Martin, maybe
yeah.
On your screen, you have like a black boxes, probably it's Zoom. So if you're able to like put it somewhere outside or just move it a bit like out screen.
Yeah, let's see. It is Alex that doing the presentation. So let's see. He will fix.
Was that better? Was that better?
Yes. Now it's perfect. Yes.
Okay, great.
Yes, sorry for interruption. You can start. Yeah.
Of course.
Good. So I think that Alex, we can go to the next one there.
Yep.
Next slide. So first we will of course introduce ourselves, and I will start. My name is, as said, Martin Johansson. I work as early engagement team leader here at PLM Group, and I'm located in Värnamo, Sweden. And early engagement for us is that we distribute the licenses for education, for research, but we're also very connected to our SolidWorks for Startup program. I will talk a little bit about, but that is what I do the most of my working days.
And my name is Alex. I work as an application engineer for PLM Group, which basically means that I spend a lot of time with SolidWorks, doing a lot of trainings. And as MarTe just mentioned earlier, I also do a lot of certification. And I have spent right around 14 years with SolidWorks right now, and have conducted hundreds of trainings and also a lot of webinars like the ones we are looking at today. And I am very happy to be able to show you some of the features with SolidWorks 2026.
It was also very nice, very pleased to see Modis talking about the certifications. That is something that I also push the educational institutes to really use to help the students to become as good as they can within SolidWorks, and also use it when they are searching for their work opportunities. And it can also be used as a quality stamp, even if you are a experienced user. It's always nice to have a certification that can prove how good you really are. So, but what we do at PLM Group is that we empower your value chain, we say. So we provide software solution and expertise to support organizations to develop and manufacture innovative products. So with our help, users become more agile with efficient operations, which will lead to a sustainable product development model. Next slide will...
Oh, sorry. Give me a second. There you
Yeah,
go.
no worries. Perfect. So short about PLM Group in numbers. We are a quite large organization. company. We have 190 employees, and we are spread in the Nordic and Baltic countries. So we are in Latvia, Estonia, Finland, Sweden, Norway, Denmark, but also on Iceland. And we speak 9 languages, which means that we are able to support in local languages, which is very important. Unfortunately, not today we got any of the local resources in Latvia to join this because they were occupied with other work tasks this day. We are very proud with our customer satisfaction, which means that they give us very high grades when it comes to our support and trainings and consultancy. And as you can see, we work with a lot of SolidWorks users out there, more than 12,000, and they are being helped by our more than 60 own software experts, and all of them have different kind of certifications in different specialties. So this is our value chain. We talk about design, simulation, CAM, PLM, and 3D print. And I will just briefly explain each section of those. So if we look at design, we help them, the mechanical CAD users design with SolidWorks, CATIA, and DraftSight to bring their products to the market faster. And we make sure that they have the correct CAD tools for their design needs, no matter what the size of the company is. And we can, of course, help to expand when that is needed. So we enable the engineers to design and create innovative products by providing the CAD tools needed to take the initial steps from design and then collaborate across functions and different stakeholders. So by connecting the design and the team in a common platform will increase the efficiency of the design part. Simulation have become a very important segment. It is, of course, very important when you design that you also have the opportunity to test and validate the products before they become real-life products. So we can predict this real-world performance virtually by simulating how the products will behave. And we have the top-tier expertise in simulation software and techniques that can help you to become as good as possible in the simulation part. CAM is another segment, and we are a trusted partner to SolidCAM. And as you know, every minute counts, and of course, every CNC machine must also be used to the very maximum. So we empower to optimize efficiency and minimize the downtime in the production for the simple as well as the most complex products needed to be used by using SolidCAM. They are customized to address specific challenges and to achieve the competitive workflows. And also in this segment, we have our own experts with many years of hands-on experience that can help. And the last part of the value chain here is the PLM. And by using PLM, product lifecycle management, we ensure that innovation flows seamlessly from the idea phase to the impact creating value across the entire product lifecycle. And also here we have the best practice frameworks and the scalable technologies. And our platform 3D Experience will help to align the people, processes, and data, all from the customer concept out to the customer. As said, we are local, so we operate across the 7 countries. This to ensure the seamless support wherever you are as a user. So 190 engaged employees. Very proud of our customer satisfaction that is on the level of 98%. We have, as said, offices in the Nordic and Baltics, at least one in each country I mentioned, except Iceland. We don't have any office there, but we distribute the licenses from our Norwegian office to Iceland. And we, of course, offer the opportunity to scale as a company and use and make sure that you are future ready. And finally, I want to talk a little bit about the SolidWorks for Startup program, because that can be of interest in this forum. So SolidWorks for Startup program is, as said, a fantastic opportunity for newly founded companies where they can take their ideas to real product and become a business. And the startup program actually includes free SolidWorks licenses, simulation licenses, licenses for visualizing the products, and also, of course, access to the 3D Experience platform. It is basically a 3-year program where you start with free licenses first year, then you have high discount on year 2 and discount on year 3. This to really help you start the company in best way. We of course offer our local support. We also do co-marketing opportunities, which means that we do marketing cases together with our startups to showcase their products and their ideas. And we offer this design guidance from SolidWorks engineers, our own or other ones that are out there in the different communities. And who can apply to this startup program? It is, as said, for the newly started ones, so not older than 3 years, but we used to say not older than 5 years. So that is perfectly fine as well, but less than 1 million euro in total revenue and less than 1 million euro in fundings. And you, of course, need to develop a hardware product. So the SolidWorks for Startup program is not for engineering services, and you should not be a SolidWorks customer before. So I think that this is a quite natural step when we are talking about how to provide students with licenses, with the opportunity to get certified. And if they want to try to start their own company, they can, of course, use the SolidWorks for Startup program. But as said, it is very important to remember that even most experienced SolidWorks users that have been working within the industry for many, many years also start their own companies and search for the SolidWorks for Startup program. So that was all from my side. Once again, trusted by our industry-leading partners. You might know these logos, Dassault Systems. They are the owners of SolidWorks, Simulia, CATIA, and then we also partner with SolidCam. We have experience in the 3D Experience platform to help customers to start to use that. And it is actually so that every new SolidWorks license that has been sold from the 1st of July 2023 come with access of 3D Experience platform. So it is now a natural part of the SolidWorks license. And DryWorks is also a partner that we work with when it comes to design automations.
Okay, Martin.
Yeah.
Thank you. All right.
Let's go well. Thank you.
Thank you. Okay, so I'll just go ahead and jump straight into showcasing some of the features you'll be getting with SolidWorks 2026. So the next couple of slides will basically be all the new stuff that has been added to the newly released version of SolidWorks, which is the version 2026. And as Martin mentioned, when you acquire a SolidWorks license, you will also gain access to the 3D Experience platform. The 3D Experience platform is a very large platform of a lot of handy tools, especially when it comes to handling the life cycle management of your products, but also enhancing communication regarding the products that you are designing. With the 3D Experience add-in, a bunch of new features has also been available for the SolidWorks installation. And one of the features that we were very proud to announce last year was a beta version of auto-generating drawings. So I remember MarTe talking about some drawings and that there might be some issues with the level of quality that comes with the drawings. Some other honorable mentions is the brake line dimension. If I were to add the entire list of all the enhancements that we find on the drawing side of SolidWorks, it would be a very, very large list. So I've spared you from that. what I basically want to highlight is that the visuals within the SOLIDWORKS drawings in 2026 has been greatly enhanced, which will hopefully assist and support the engineers in being able to produce some very, very good looking drawings for both company and customers. So there's been a lot of improvements on the visuals of the drawing layout in SOLIDWORKS 2026. But before we continue, let's have a quick look on the auto-generate drawings. So we have come up with a model for today's webinar. We've tried to model what resembles an engine bell from a rocket, together with a turbo and some mounting brackets. But for this one part, I would like to try and showcase the auto-generate drawings. So let's say that I'm happy with the way my model look right now, and I want to generate my drawing, but I haven't got the time to do it, or I want to hurry up and create something for the production line or customer that they can look at right here and now. I can go ahead and click the auto generate drawing. You can see it's in brackets beta because it'll be upgraded this coming Saturday. I'll get back to that. But I'll just go ahead and click this button. It'll ask for a title and a name. I'm happy with the name it's got right now, so I'll go ahead and click OK. And on the right-hand side of SOLIDWORKS in our task pane, you can see that we have the auto-generate drawings. We have a title, it's the Raptor, a status icon that is slowly loading. I'm not entirely sure you can see this on the stream, and then I'd be able to cancel it. The cool thing to note is that I'll be able to continue to work with my model in SOLIDWORKS while the drawing is being generated in the background of SOLIDWORKS. So I'd be able to continue designing, engineering, creating features, or even go for a cup of coffee whilst my SOLIDWORKS software is slowly generating the drawing. As I mentioned, this feature is right now in a beta version, which is sort of like a work in progress. I am sure you're familiar with the term. But this coming Saturday, so only in a few days, an updated version to the automated drawing will be released with the first service pack of SOLIDWORKS 2026. So status says it's complete, and I'll be able to click open. Since this is a fairly large model, it's a 1-to-1 scale, the individual views of the part is right now somewhat small, but what I can conclude is that the drawing has been able to create some section views for me. It's also been able to import some of my dimensions. I know that all of my dimensions are not here. It is possible to go ahead and modify the information that the drawing will generate for you. But I mean, this is going from absolutely zero automation to the first automation in SOLIDWORKS generating drawings. So this is basically free for me. I can sit back and relax knowing that the drawing is now, it's got some information, and I'd be able to go into my drawing now and then add some more information if I want to. I can also go ahead and delete some views if I don't need it. Anyways, it's still in a work in progress, but it'll definitely save some time for you, and it'll be continuously improved going forward. Okay, so coming back to our PowerPoint, we will be talking about another AI that's been introduced to the 3D Experience platform, and the name of this AI is Aura. So Aura is, for the most part, a chatbot on our platform. And some of the updates to Aura is that Aura will now be able to summarize a lot of information. So right now we're looking at a very large design specification from a customer or a project. And with Aura, we have the feature like summarize, which will basically shorten everything down. Aura will also be found within SOLIDWORKS, so you can see from here We are inside SOLIDWORKS software, and we've asked Aura, how do I save this document? A fairly simple question, some would argue, but Aura will give you a very thorough 8-step process of how you can proceed with saving this exact document. So with the introduction of 3D Experience, we have now also introduced some different AIs into our software. All right, the next stuff we will be looking into is some assembly, some assembly updates to the 2026 release. What is noticeable is the split configuration and also the fastener automation. So within SOLIDWORKS, we obviously use a lot of fasteners and a lot of bolts and a lot of nuts. And these are usually taking up a lot of work time, making sure that every bolt and nut is positioned correctly within our assembly documents. But hopefully with the new 2026 version, you will realize that the AI will now recognize geometry and automatically attach a nut or a bolt to a hole in our assembly document. First of all, I would like to just quickly jump back into my part. Go ahead and close my door, because one of the other news was that for this model right here, I have modeled it both with the turbo and without the turbo on the right-hand side. And when I'm done modeling this one part here, and I have a bunch of different configurations. Right now, I only have 3. But let's say I would like to go ahead and create this one part of its own. I can go ahead and right-click the configuration, and I can select split configurations. When I split the configurations, SOLIDWORKS will then also acknowledge that there is a drawing attached to this one part, and I can select whether I want to keep it or not. In this instance, I would like to keep it, and when I click Save, SOLIDWORKS will split all the configurations into individual parts that you'll then be able to work with individually. Coming back into our presentation, give me a short second. We will have a look at the assembly updates that I just mentioned. So another thing to have a look at is that working with assemblies usually is a very tedious, time-consuming work, because whenever you update a model, you'd have to update the assembly that the model is referenced by. But with 2026, there's been added some new ways of handling local updates on parts that are contained within an assembly. So if you only do graphical changes to a part that is within an assembly, the assembly does not need to be reloaded and saved like it was back in the day. And all of the work going backwards and forwards from part to assembly is very smooth. In this situation right here, we can see how the engineer is working with very simple parts. So this is not a smart or intelligent part. This is just a part that has been created by an engineer. And as you can probably tell, he is very seemingly just dragging and dropping the components even from the Windows File Explorer directly into SOLIDWORKS. And as you could probably tell, the components will automatically try and snap to some geometry that it recognizes as being a counterpart. So all of this is basically what can be classified as AI recognition of geometry within the SOLIDWORKS software. Next thing we will be looking is going to the 3D Experience platform. So we have this very large auto camber that we will be working with today. But the work that I will be doing with this auto camber only consists of a few of the parts that is within the auto camber. So before I open the auto camber, I'll just go ahead and select it. This is in my browser environment. So I'd log on to my Google Chrome or my Microsoft Edge. I'll go ahead and I'll find my a large assembly, and then I'll go ahead and add a filter. So I'll go ahead and filter all of the components that I need to work with today. And when I'm happy with what I've selected, I'll go ahead and save this basically as a view, or as it is called right now, as a filter. So I'll just go ahead and name this filter as fridge piping. And when I'm done with that, I'll come back into SolidWorks. So I did all of the work in my browser, but now when I load it from SolidWorks, we can tell that the information that we created or generated in the browser environment is now accessible within SolidWorks. This will greatly enhance the, so to speak, performance issues that might occur when working with large assemblies. In this way, you don't have to open a very large assembly document, then go ahead and suppressing a bunch of stuff. You can go ahead and basically select only a couple of components that you need to edit, and then save them in a browser environment, and then afterwards open it in SolidWorks. This will hopefully streamline your way of working in SolidWorks quite by a large mile. Okay, so with SolidWorks 2026, we've also had some changes to the import performance. We know that a lot of people is working with step files in particular. Step files is sort of like a native language to share geometry from one computer to another computer, especially if the people that you're working together with do not have access to SolidWorks. Stepfile has notoriously been here for many, many years and is a well-supported platform for sharing geometry. But step files also tend to be fairly large. They also tend to take quite a lot of time to open, also in SolidWorks. So one of the new stuff that we've added for 2026 is that when you open the step files, you'll be able, as you might be able to tell from the bottom right-hand screenshot, you'll be able to go ahead and filter components by the size of the component. So in the bottom right-hand corner, there's a picture of a model, and the model contains quite a lot of unnecessary geometry that we don't need. So there's a lot of nuts and bolts within this step file, and we will be able, when opening the component, to go ahead and deselect all of these components, which will then eventually lead to the case that there's not a lot of information that needs to be imported into SolidWorks, and it'll make the import process very smooth. But coming back to SolidWorks quickly. So the auto-generate drawings, we already talked about that. And with that feature also comes an import model in background. So this is, again, SolidWorks will be able to import a large geometry. And if I just go ahead and find a step file, like so. So SolidWorks is now opening the step file right now, but it's doing so in the background. And as before, when I was creating a drawing, I will be able to continue to model my SolidWorks part. And right now in the background, SolidWorks is now importing the step file. So this took 17 seconds. It's not necessarily a large file, but you can imagine looking at your SolidWorks trying to import a very large step file that takes minutes, and we've seen hours from very large files. But from 2026, you'll be able to just go ahead and import in the background, and then you go ahead and click Open File. And when you click Open File, everything is ready to go ahead, and you can start engineering on your step file. So also a very handy piece of sort of like background piece of software that came with the SolidWorks 2026. Coming back into the presentation, we are now looking at some of the components that we have stored basically in our cloud environment, the cloud environment being the 3D Experience platform. We saw some changes to the 2026 SolidWorks 3D Experience, which was the ability to go ahead and save configurations as well on the platform, as I just showcased within the software. So this feature was introduced not that long ago, and it took some time to develop this piece of software because the 3D Experience platform, being a browser and cloud environment, handles our files in a different way that we are used to working with them on our local C drive on our individual clients. All right. Yeah, I've already showcased the split configurations, but I would just like to mention it for one last time. It is a very, very handy tool to work with a lot of different configuration that represents our product, maybe in different states of the life, maybe in different ways of production. And now with the introduction of split configurations, it's just been very, very easy to go ahead and proceed and utilize all the different configurations that you've been working with. Back in the days, you would imagine that you've built one model and then realize that you'd have to build another model either the same way or in a different way. In this way, you can create a large model file set within one, either assembly or part, and then afterwards you'd be able to go ahead and just split it into multiple different individual parts. One of the new, basically talking about the 3D Experience platform. 3D Experience platform is also focusing a lot of connecting people. So traditionally, when working with CAD files across multiple different users and customers and companies, you are basically used to generating files in SOLIDWORKS, saving them, and then distributing them either as a step file or a pack and go. You will probably today you will be using softwares like Microsoft Teams to share documents, or you might be using any other kind of cloud service. But even as practical as a Microsoft Outlook, basically just emailing stuff in between different partners. With the 3D Experience platform coming into SOLIDWORKS, as you can probably tell from the picture we're looking at right now, we are right now within the SOLIDWORKS software as you are used to, but as you can tell from the right-hand side in what we call the task pane of SOLIDWORKS, you can tell that we are looking at some forums. So these forums has been added to the SOLIDWORKS interface, and it'll basically allow you to communicate directly from the SOLIDWORKS software. So let's say that you are experiencing some issues and you don't know how to proceed. You can basically go ahead and ask the question directly into the SOLIDWORKS forum, and you can attach a screenshot of your model as well. And in this case, Debbie Designer was very lovely and answered us with a question saying, have you tried to use the feature break view? And we tried to use the feature break view, and in this case, that was exactly what we were looking for. So we'll give Debbie a thumbs up, as you say, and we will go ahead and validate the answer she gave us as making sure that this was the correct answer for this specific case. So in the future, if people are in the same situation that we were in, they'll be able to see that once Debbie answered this question and it helped us as Eric engineer, and everyone else in the future will be able to go ahead and use the same solution as the one here. So the 3D Experience platform is definitely trying to introduce a lot of modern technologies, both with AI features, but also trying to basically expand the forums and the communities surrounding and revolving around SOLIDWORKS, basically trying to bring everyone closer together. All right, so unfortunately, a couple of years ago, we somewhat lost the possibility to create renders within SOLIDWORKS. There was an update to SOLIDWORKS, I believe it was 2024 maybe, we lost the possibility to create renders within SOLIDWORKS, but coming SOLIDWORKS 2020-2026, the feature has been added into the software, back into the software again, and this time around it's even been greatly enhanced. So some of you might know the software called Visualize. Visualize is a rendering software that'll be able to create some very beautiful pictures of your SOLIDWORKS models. All of the pictures that you see in the right-hand side of your screen right now has all been generated within SOLIDWORKS Visualize. The model you are looking at is one of the SOLIDWORKS customers that uses SOLIDWORKS to design their Vermeer digging machine. And these pictures has been rendered within Visualize to create some very nice material for both the marketing but also the sales department. And as mentioned, the render possibilities has been reintroduced into SOLIDWORKS, but now also enhanced, which means that the SOLIDWORKS Visualize engine is basically being used within the SOLIDWORKS software right now. So back in the day, so to speak, you'd have to basically somewhat export the document into Visualize, creating your Visualize setup and then rendering the picture, but most of the functionalities from the Visualize software has been attached to SOLIDWORKS directly. So what we look at right here is attaching some very beautiful surface treatments to our model, and as you can probably tell, the enhancements regarding the surface finishes to the material has been enhanced quite a lot. So it almost looks like that there is a 3D mapping to the parts that we are looking at. It is not a 3D map at all. It's just basically been enhanced with what's called DSPBR technology, which makes it look very natural and very lifelike. After this, we will just go ahead and add a background to our SOLIDWORKS viewport, and then we'll go ahead and create the final render. The final render obviously takes a couple of minutes, but I will spare you that. So we'll go ahead and set it to a high quality and click OK. And basically, this took right around 4 to 5 minutes, I think, rendering this picture on my PC. So this will obviously differ from PC to another according to your hardware. Okay, another feature that is very handy to look at is the share feature. Because we would love to share our documents with external partners, we will be able to share files in many different ways. One of the ways that we can share our files is with the share and with the share command within SOLIDWORKS, and we'll be able to share our files with people that don't have SOLIDWORKS installed, which means that we'll be able to share this document, and the person that we are sharing the document with will be able to open this document from a browser environment and look at the model right here. So the new share command will be introducing a process where the recipient do not need SOLIDWORKS to look at the file. The recipient will only need an internet connection and a browser software. Looking at some of the simulation enhancements for 2026, we have some rotational displacement plots, and we have improved on the shell formulation within SOLIDWORKS, and also added some pin connector forces. So we'll be looking at this one model right here. So this model is obviously a very large sheet metal model. A sheet metal model is notorious for being a geometry that is fully drawn, so there is an inside and an outside of the model. But with the shell improvements in SOLIDWORKS, we'll now be able to just go ahead and remove basically all of the inside to the geometry and just defining a thickness which makes the simulation run extremely more quicker than we are used to. So for this study, we have selected our pin as the connector, and we have a coordinate system that we will apply a load to. So with the load applied from the coordinate system to the pin, we'll go ahead and click run, but unfortunately we have an error. So apparently one of our components is missing a material, and from 2026, SOLIDWORKS will now very helpfully explain us which material is missing from what part, and we'll just go ahead and reattach some material, a plain carbon steel, and then we'll go ahead and run the study again. So when we run the study, we will see that the results of this study is somewhat not acceptable. Apparently, there is quite a lot of displacement. We'll go ahead and look at the rotation around the y-axis, and we'll go ahead and change it from rads to degrees, and then we'll go ahead and just have a quick look at the animation. And from this simulation, we are not happy about the forces. The forces is definitely too large on our component. So we'll go ahead and jump into our shell manager. So inside our shell manager basically consists all of our bodies within the model, and it's very easy for us to just go ahead and change the thickness of the entire model from 0.25 inches to 0.625 inches, and then go ahead and run the study one more time. So in the meantime, we've changed the thickness of our sheet metal, and from the new results, we can tell that the simulation is much better. What we would then love to, or like to have a look at, is the new vibration plot. So the connector, the pin that was connected to the force, or the force was going straight into one of our connector pins, we can now also have a look at our vibration, our vibration graph. So apparently there is quite a lot of vibration when it comes to a specific point of hertz, and that will then be taken care of by the engineering department. All right, continuing on, I know that we are running a little low on time. I'll try and make it quick from now. We are now able to also include a lot of information regarding our weldment information on the 3D Experience platform, which basically again goes to show that we are now able to share a bunch of information regarding our SOLIDWORKS products directly to a browser environment, which makes it accessible for everyone in the company who is logged on to the 3D Experience platform. I have a question. I still have a couple of slides left, but I know that we might be out of time. Should we continue on from here, or how should we proceed?
I think you could show the slides. I think we can spend a couple minutes more, so it's not a problem.
Okay, thank you. Thank you. I'll continue. Obviously, there's been some improvements to the performance within the software. The software is always updated. The software is always being more streamlined. So here's the comparison from SOLIDWORKS 2025 to SOLIDWORKS 2026. And in this one case, we saw an upgrade, or basically an enhancement of 30% faster, basically from the same software, but just the software engineers improving on the codes within the software. Design tables, basically the same as the weldments that I talked about earlier. Design tables can be generated from an Excel document. So the Excel document will be making sure that the actual design or the geometry will change according to the Excel document. You have probably already worked with this earlier on. So we are now able to also attach the Excel document to the file that is stored in the cloud, and everyone will be able to access it also from the cloud. These enhancements were also seen in SOLIDWORKS 2026, basically trying to accommodate what you are used to. All of these features are being moved from basically your local client into the cloud as well. Deformable components, I think this is one that we will skip for now just because of the times. One very, very interesting one is the iteration comment. So obviously when we are designing our model, we have a lot of iterations, we had a lot of versions, we have a lot of revisions, and we also have a lot of what's called branches within the 3D Experience platform. The iteration comment is basically whenever you save the document, you will now be able to go ahead and add a comment to what changes you have made. And as you can tell from the right-hand side of the document right now, you will be able to scroll backwards and forwards of the individual iterations that you have made. So you will be able to very quickly go back to another time in life of this one product. And if you want to navigate it smoothly, there is the possibility to add a comment of how the part looked back in the day, so to speak. So iterations basically regarding the life cycle management revolving around the parts. There's a bunch of possibilities with the 3D Experience platform as well. My last two mentions is that coming this next Saturday, as I mentioned, we have a big release for SOLIDWORKS 2026. And this Saturday, we will see a new AI being introduced into the software. The other AI I mentioned was named Aura, and the new AI being introduced is named Leo. So Leo will be adding two very important things into SOLIDWORKS. One of them is the assembly structure assistance. Basically, we have a chat with Leo in the right-hand side of SOLIDWORKS specifying what we would like to build in SOLIDWORKS, and Leo will then go ahead and try, as you see from the middle of my screen, will try and build an assembly structure of all the parts necessary for building the actual product that you are looking at. Another enhancement coming with Leo this Saturday is the what's wrong analysis AI, so to speak. So whenever you have an issue within SOLIDWORKS and you are struggling to try and figure out what is wrong and why am I not able to fix my model, Leo will try and help you using some AI-powered engines, and you'll be able to ask Leo what is wrong. And as you can tell from the right-hand side of my screen, Leo will try and guide you through the processes of fixing your issues. And with that, sorry, I know I surpassed the time limit, but with that, that was what I had for SOLIDWORKS 2026.
Thanks a lot. Thanks for you and for Martin as well. It was very interesting and hope very useful for our colleagues as well. Maybe a couple questions if someone would like to ask. I hear no response from audience, but I have my questions. Martin, maybe again highlight from your side about startup involvement. So you propose up to 3 years discounted like a license for startups. So its first year is completely free for startups, and startup not longer than 3 years. I think this could be very, very useful for MarTe project and MarTe community, because we are interested to drive technologies to market, and we are interested to bring new industry players and exactly startups, students and engineers who are interested in doing their business and doing business in deep tech. And we probably try to promote your advertisement about startup users in much better auditory. Yeah, so it's maybe just comment that this is a nice feature, and thanks for it, because again, I personally know for small companies it's quite tragical actually to buy a full license. I know you have like a couple weeks free demos or something like this, but sometimes it's completely not enough. And maybe a question to Alex as well. Nice to see IE in like build it in SolidWorks, but is it cloud-based? So you anyway need internet and connection to use this. Is it right? So it's not a particular computer.
Yeah, somewhat. Some of it is cloud-based, and some of well, basically, you would need the 3D Experience, which is a third-party software, so to speak. CAM Visualize Simulation is also a third-party software to SolidWorks, and the 3D Experience platform is also an add-in you would go ahead and download from SolidWorks software. You would install it on your computer, and when you install it on your computer, you basically gain access to all the features provided by the 3D Experience platform.
Perfect.
So,
how it's actually stable? So in sometimes using IE, it make not saying errors, but going somewhere wrong direction, and you need to bring it back. So let's say, for example, of automatic drawing recognition and model building, how your experience, how good is it?
Yeah, so first of all, I've only been working with the auto-generated drawing since the release of the beta version back in November of last year. So it is very, very new. I know that the auto-generated drawing is basically building a drawing from your default template. So the better you also, or the more time you invest into building a very nice drawing template, the better the AI will work together with you. But also, as I mentioned, it was a beta release right now because SOLIDWORKS 2026 is in a Service Pack 0.0. So the Service Pack 1.0 is coming this Saturday, and with that, there will also be enhancements to the auto-generated drawing. So the drawing will not be 100% complete. You cannot leave your head and just click the auto-generate drawing and then go home. But it'll definitely give you quite some free time to continue working with your models since the drawing has been generated in the background. And we will only see improvements, and you will also manually be able to tell the AI, I would love for you to import these specific annotations. So as a user, you are also able to model the AI into, making sure that these dimensions is definitely important to me. I would love for you to import these. But probably in the future, we will see that the AI will be better at recognizing all of the necessary dimensions to introduce into the drawing.
Okay, thanks a lot. And we're becoming short of time. So thanks for you. And actually, I would like to say thanks for Kasper Ieselnieks from Latvian Thermal Group. He's helped us a lot to setting our computer class. So respect for this. And so we will keep in touch. And thanks for joining our webinar and workshop as well. Yes, so thank you. And
thank you and bye.
Try to finish our morning session. Now we will have a lunch, and lunch will be until 1 o'clock, and we continue our seminar with more examples, not like an overview for software, but practical examples of what we can do with numerical modeling and modeling itself. Again, so I will try to share my screen and put a program. Please return at 1 o'clock here, or stay connected in Zoom. And people who are willing to participate in hands-on activities can give me note, or again stay in Zoom, and we will guide you in hands-on activities later at the end of the day. Yes, so any questions, comments from auditory? No. Okay, so you're welcome to have a lunch. Lunch will be provided here just in the corner, so in the next room to this auditory, and we will meet here at 1 o'clock. Hello, so we are going to start afternoon session, and Christian, are you here? Christian, are you here? Christian? Christian, nice to hear you and see you. Do you hear me? Christian, do you hear me?
Hello?
Hello, do you hear me?
Should I hear you? Or what's the...
I hear you perfectly and see you as well, very nicely.
Yeah, I can't hear you. I wonder, is it my problem? Can you hear me at least?
So I hear you, but...
I wonder what's the reason. Because obviously my...
So I hope I still
typical start. Okay. Yeah, I think now I can hear you, yes.
So you hear me? Okay, good.
Yeah.
Nice to see you and welcome to our workshop. Yeah, so I will stop my screen sharing and I think we may wait a minute and you can start the presentation.
Do you now see my presentation?
I see your second screen.
You see my second screen. You see this one. Now it's better.
Yes, now it's perfect. But some Teams alerts as well on bottom of the screen.
Sorry, I tried to share different screen then because
no, it's perfect. No, it's fine.
No, is it?
No, not now. So it was nice,
No.
but now you switch to another screen again.
No, yeah. Somehow with the free screens, everything goes so much more complicated. So now it should be perhaps a bit better. So now it's only the presentation, nothing else.
Yes.
Okay, very good.
We see your presentation, and couple persons missing, but I think we can start. Okay, so Christian, thanks for coming, and I'll try to announce you. So Professor Christian Tabri from TalTech, Estonia. Welcome here in Ventspils, even remotely. Yeah, let's start. I see mine.
Yes. Okay. Good afternoon, everybody. My name is Christian Tabri. I'm a professor at the Tallinn University of Technology and its Maritime Research Unit, Marine Technology Competence Center. And I will now spend about half an hour to talk about how we can exploit contemporary tools, modeling and simulation tools, to simulate what has happened to a vessel which sank a bit more than 30 years ago, and really to show how much we can learn at the moment how the vessels behave using modeling and simulation tools compared to the situation when this vessel was designed and built. So I'm talking of this vessel Estonia that sank on September 1994. It had a bit less than 1,000 persons on board, and out of those 852 died and only 137 persons survived, because the vessel sank in the middle of the sea in very harsh conditions, and it sank quite quickly. And of course, after the accident, there was investigation. What went wrong? Why such vessel sank? And what could be done differently in future? And official investigation was already published in '97, and this then stated that the main reason was that the bow visor of the vessel detached under the wave loads, and this opened the access to the water car deck. And of course, when the ship got flooded, it didn't have enough buoyancy to stay afloat, and that's why it sank. And of course, there were always a lot of rumors or speculations around this accident. Was this official cause really what actually happened, or was there something more involved to this accident? And actually, in 2020, there was new video footage which showed that the ship had quite a large damage on its side. And of course, there has always been speculations that there must be a collision with, I don't know, some submarine or some explosion somewhere, that there must be something which made this ship to sink. And it was not only the bow visor what was the reason. So yeah, those new video footage became available in two reasons. First of all, our technology has improved so much more that we could go into 80-meter deep water and get very good camera image from this water depth. And another thing is that over the time, the vessel had rolled a little bit in the sea bottom. So it had revealed what was under the vessel. And of course, this fueled really a lot of new speculations, kind of that, hey, we told you that there must have been something strange with this accident, because now you see that there are side opening, and this is the reason why this vessel sank. And this then resulted in new investigative activities in 2020. So quite soon it was decided that the preliminary investigation has to be conducted to understand whether the whole investigation of the accident should be reopened. It's a little bit like official terms on between those accident investigation bureaus. So this initial investigation has now taken 5 years. Now it has been completed, and we can then draw the conclusions what we found out. And the aim of this new investigation was then to collect the new evidence and really to model more or less the whole accident, how it happened. And the investigation include quite a lot. It include a lot of surveys at the wreck site, sea bottom studies, wreck studies. A lot of different robots were used. The bow ramp of the vessel was taken to the surface for the investigation, and the whole ship was really scanned in as detail as possible to get the full 3D image of the shipwreck as it lies in the sea bottom. And of course, this gives us a lot of information or the validation data to see that if we simulate something, do we end up in the same condition and the situation what we see there at the moment. Of course, we have to keep in mind that 30 years has passed, so the vessel has shifted in the sea bottom. It has degraded further. There is some corrosion. Of course, it's 80 meters deep in the sea bottom, so there is not that much oxygen there, but still some oxygen for the corrosion. But anyway, a lot of evidence was collected. Quite some material was brought on the surface, which then could be used to validate and to see how well we can simulate this accident. But a little bit of the background for the accident. The first Ro-Ro ships appeared in the Baltic Sea in 60s. Yeah, it was quite a new vessel type where the cars just roll on the ship deck, and also it takes on board the passenger. So it was quite a novel ship type in the Baltic Sea. And Baltic Sea is a little bit specific with its relatively short and sharp waves. But it turned out to be so suitable vessel type for our waters. So this number of ships started to increase with enormous pace. And actually the increase in the numbers of these Ro-Ro ferries in the Baltic Sea was the greatest in the world. So nowhere in the world did this ship type see so large usage as in the Baltic Sea. So for example, at the beginning of 1960s, 900 trucks was transported by the sea. But in the middle of the 90s, it was already 140,000. So you could imagine how much more capacity there was at the sea to transport all these trucks. The ship itself was built in 1979, so it was designed then a few years before. And you can imagine how the computer looked at that time. So you didn't have this amazing set of tools and computational power or artificial intelligence nowadays. Then your Apple computer looked like that. So you didn't have that many tools to design the ship. It was mainly paper and a pen what was used for the designing. And also the numerical simulation methods did not really exist at that time yet. They were there in the universities, maybe in some bigger aeronautical companies, they used already some of the simulation tools, but in the marine engineering field, the numerical tools were not really used because they were so new tools, there were no computational power, so it took 15 to 20 years before the numerical methods, what we use nowadays to design ships or maritime structures, really started to have their role in the engineering or maritime industry. And yeah, we talk about computational fluid dynamics to simulate hydrodynamic loads on the ship. We talk of finite element method to simulate how the ship reacts to the loads, or fluid structure interaction methods that then allows us to put together the water and the structure. So these methods were not there when the ship was designed. Also, that kind of progressive flooding simulation softwares, which allow us to simulate in very complex ships like the ro-ro ships or ropax ships or cruise ships are, how the water, if there is some accident, how the water flows or moves inside the ship. These tools started to emerge only in the middle of 2000s. Before that, it was very hard to assess such complex ship, what would happen if it gets flooded. So there was quite limited availability what you could use. And the accident itself happened in 1994. And then this first official investigation report, this was then published in 97. But what was this really an isolated accident? In the Baltic Sea, actually, there was a lot of accident with this ship type and a lot of accident with the visors. So each of these red dots basically indicates some issue or some accident with a bow visor of that kind of vessels in the Baltic Sea. This one, which happened a year before Estonia accident, this was also actually quite serious. I think the ship basically lost the whole visor. But at that time, this information was kind of hidden. It didn't go into public that well, and no one really knew that much of these accidents because all the ship owners tried to hide the facts that they had some problems with their ships. And actually already in 1986, so 8 years before the accident, the ship owners agreed that they will not build anymore the ships with that kind of structural configuration because this configuration is not good enough. So the knowledge was there, but the ships, of course, still kept sailing. So basically what we could say that these ships came to market because the economic competition was so harsh and there was so strong need for the vessels. But really the scientific knowledge and the design methods and the simulation tools, they didn't really pick up. So there was no tools to understand how these ships would behave in the Baltic Sea. And actually Estonia had very poor design. It had, how this visor works. The visor opens, then the car ramp is lowered and the ships would go into the car. In Estonia, the design was such that the car ramp was relatively long. So it means that this car ramp had to be fitted partly inside the visor. So it means if the visor falls off, it pulls open the bow ramp. But the bow ramp for this ship acted as a collision bulkhead. Ships require a collision bulkhead that if something happens in the bow part of the ship, then this collision bulkhead should prevent the water entering the ship. But in Estonia, this collision bulkhead, which was the bow ramp, the design was such that if the visor failed, the collision bulkhead also fails. So if one piece falls off, then your enormous car deck is free for the water to enter the ship. Little bit, what's the situation at the moment? At the moment, seagoing ships can't have the visors anymore because the design is not safe enough. So here is a ship with a visor. If you go to a modern ropax or ro-ro ship, you don't see a visor that opens up. You see the bow doors, which opens sideways, and the cars enter through these bow doors. What's the principal difference between those two solutions? For the visor, the wave loads try to open the visor because they try to push it up, this rectangular part. For the bow doors, the waves try to close the doors because you can imagine the doors are here, waves are pushing against these doors, and it pushes the doors next to a ship hull. So much safer solution compared to a visor which has to fully open. So now all the ships which go far to the open sea, they need bow doors instead of visors. But anyway, our aim in the project was to really simulate this whole process. So we did quite many different simulation models. We started with wave loads that were acting on the visor. We looked on the model scale experiments, which were done in 2007. We prepared so-called computational fluid dynamics model, which allows us to simulate the wave loads numerically acting on the ship. We also prepared so-called multi-material arbitrary Eulerian model, which allowed us to evaluate if the visor was already open, how much the loads changed in that condition. And when we had the loads, we had very fine finite element model of the bow area of the ship, where we then applied those loads. They are waved, they come and go, they come in sequences. So, sorry. We could then apply these loads to the visor and see how would be the visor respond, and whether the wave loads, what we estimate that they were there in the night of the accident, whether they are sufficient to break the visor structure. And then we also prepared the whole ship model to simulate the bottom contact to see whether it's possible that those damages, what were really found in these new video footages, is it possible that they occurred when the ship hit the sea bottom? So basically that they had nothing to do of the sinking of the ship, but they already occurred as a consequence of the accident. So computational fluid dynamics simulations look like that. You have a ship, you have a waves, and you can then see what's the pressure distribution, and how this pressure correlates to different wave heights and wave directions. So you could get quite good understanding what's the loading condition in your bow structure. We also then did a bit more complex simulations where we were modeled a bow visor as a separate part from the ship so that we could allow it to pivot. Because obviously when the bow is closed to the ship, the visor is closed, it experiences some kind of loads, but when it's already allowed to move, the load level drops a little bit because the visor simply moves away from the waves. So this was just, we needed this to construct the realistic load sequence so that we could really start simulating the process when the visor is fully attached until when it's really torn off from the ship. Yeah, these are the details of the model. We really had to model it in very high detail. We also had to model hydraulic cylinders, how they move, how they get compressed, how they get extracted, because all this played a quite big role in this accident. So very detailed model, a lot of moving parts, like different hinges, different locks, a lot of details in the model. For the final bottom contact simulation, yeah, then we had a full ship, and we also modeled the sea bottom. During this investigation, some specimens were taken from the sea bottom to understand where we have stiff clay, where we have some softer clay, and where we have actually hard rock or acoustic sea bottom, so which is basically a rigid surface. Because where the ship lies at the moment, it's hard rock covered by soft clay, but partly this hard rock comes out from the soft clay, so this gives a very local points to the support to the ship when it's at the sea bottom. And yeah, then more or less this is how the simulation looked. We started in the condition when the ship was already approaching to a sea bottom, and then simulated how it fell to the sea bottom. I will have some videos a bit later. Also, some specimens were cut from the actual shipwreck to see what are the material properties. So we were really using the actual materials that the ship was made of. And yeah, this is now the visualization, what happened with the bow structure first. First, when the large waves hit, the first lock, which is also called Atlantic lock, was broken. Then the ship had also side locks, which failed very quickly after the bottom lock failed. Then the ship had some hinges here on the deck. These hinges were also broken quite fast. And then the visor remained attached to the ship only through those quite large actuators or hydraulic cylinders. But sorry, it's restarted. And you see that the bow, I scroll a little bit back, you see that as this visor is moving, it also pulls open the car ramp already. And the movements are quite violent. So what happens that these cylinders, which are still holding the visor in place, they are pulled through the ship basically. And in front of the ship, it really pulls through those cylinders from the forward wall or forward bulkhead of the ship. And we really see in the shipwreck also these locations where the cylinders were pulled through. So this is more or less how we foresee what happened. We also had then a lot of evidence from the shipwreck, what was left in the wreck, whether our simulations corresponded to this. Also in our simulations, we saw that the cylinders were pulled from the deck plating and pulled through the front wall of the ship. And also in the wreck, you see very clearly where those cylinders have been pulled through. So our simulations correlated actually quite well to the reality what we saw. Also, the visor itself, it has been brought out already years ago. It's in Sweden, and it has quite a lot of damages actually on the visor. And we also were capable of explaining very well from where those damages came from. One damage, which is here, came when the visor fell off and hit the bulbous bow. Then the visor rolled itself around and remained floating in front of the ship for a few seconds, and the ship hit the visor once again, causing this very large damage. But its damage shape corresponds very well actually to ship bow shape. So with nowadays tools, we could really explain almost every scratch in the paint. Of course, it's a bit of an exaggeration, but you could really explain most of the deformations, what we see in the structure. Same with the bow ramp. The visor starts falling off. It opens the bow ramp. Bow ramp also experiences different kind of deformations. And in the simulations, we could repeat those deformations quite well. Another interesting assessment what we did was that after the accident, the bow ramp was still attached to the ship. And that was more or less the initial condition. The shipwreck was in the sea bottom and the bow ramp was still attached to the ship. But now in those recent investigations, I think in 2021 or 22, they discovered that the bow ramp has fallen off. So what we then simulated that we tried to estimate where would be a corrosion damage in the bow ramp and what could be the corrosion during 30 years or 20 or 25 years. And we're simulating how would, if this corrosion has developed and the ship, and of course the ramp is still attached to a vessel, how would it be torn off from the ship? And actually, we also managed to achieve the situation, what we see in the wreck at the moment, that piece of the bow ramp is still attached to a ship but the ramp itself has been torn off. So yeah, we assumed that the corrosion is the strongest in the regions which get a lot of plastic deformations during the sinking, because that's where your paint gets damaged and you are more open for the corrosion. And also, if you look on the shipwreck, then we see that the bow ramp lies next to a ship, and part of the bow ramp is still attached through 2 hinges to the ship. Part of this is not now our work, but it's German consortium which was subcontracted by Estonian Accident Investigation Bureau. They also simulated the different scenarios. Let's say, how would the ship sink if the visor is open? How would it sink if there would be only side damage? And how would it sink if the visor is open and there is also side damage? So you could really simulate nowadays those different. You could really take the different assumptions and see how would the ship behave in those different conditions. Only with side damage, the sinking was much slower compared to what happened in reality. With side damage and open visor, it was a bit too fast. And actually, if the open visor was assumed, then the sinking sequence and duration corresponded quite well to the witnesses' testimonies. And I scroll a little bit further, but yes, how these simulations ended. And yeah, then we also conducted the simulations how the ship would hit the sea bottom. Here we only visualized the acoustic sea bottom. We have removed the soft sea bottom because otherwise it's not that easy to see what goes on there. But that's basically how this bottom contact process was simulated. And as a result of that, we could get quite good estimate for the damages, what should be on the ship structure. And we could then compare these to the basically 3D model of the shipwreck to see whether these correspond well. And yeah, also just to show that we also had this very soft sea bottom actually on top here. And this is how this soft sea bottom is pushed away. And from some regions where the center part of the ship is, you see that this acoustic bottom becomes visible. And this acoustic bottom is then this rigid bottom, which causes the main damage to the ship hull. I see that I have only 1 minute left, so I quickly scroll through a few more videos, which see how our simulations correspond to a current position of the shipwreck. Does it this brownish transparent model is the ship's current position, and in our simulations we achieved quite comparably the same position for the shipwreck. So it means that our calculations are not too off. And then we could also look locally what are the deformations and damages to the ship hull, and also what's the extent of damage in the ship. So if we cut the slices from the ship, then we see that in the middle of the ship, the damage is actually very extensive. You have like 1/4 of the ship completely pushed together. So what we could see from those videos, they present only small part of the damages, because a lot of damages are actually covered by this soft sea bottom and we don't fully see them. And yeah, also this, what we saw in the simulations and what's the actual condition of the ship, it corresponds quite well to these damages, what we have seen in the shipwreck. Yeah, very quick conclusion. I don't want to go over the time, but that kind of major accident typically means that several things should go wrong. So in the case of Estonia, yeah, you could start from that lessons were not learned. There were a lot of accidents with those visors, but this didn't come to the requirements. This didn't come to the flag state tables. So the ship owners kind of kept it a little bit hidden. Rules didn't really follow the ship type, and the rules were not appropriate for these ship types. It was a poor design. It was a poor construction as well, and perhaps also inspection and maintenance was not done as it should have been done. So quite a lot of issues which have to go wrong for that kind of major accident to occur. Okay, and that concludes my talk. I went 2 minutes over the time, and sorry for that.
No, thanks a lot. It was very interesting and very comprehensive on models what we were showing. Yeah, it's okay. A very big strategy about Estonia, Estonia. But again, it's a lot of lesson learned probably after the strategy. And
yeah, of course.
Remember, right? You show a plot with accidents. And after Estonia, I think it's much less accidents happen in Baltic Seas.
Yeah, obviously. And the ships are much more safer. There were really a lot of changes in the legislation after this accident.
And very interesting how you model so different and difficult and big constructions actually. So it probably takes a lot of time for model. Everything.
Yeah. It was quite big group and several companies and persons involved. So it was obviously a team effort. I think in addition to our university, there were 3 or 4 engineering offices involved to prepare the models and conduct the simulations. So yeah, a lot of partners to deliver that kind of study.
And maybe good outcome from it. So it was a lot of speculations about like a human factor and so on. But showing your models, it's clearly seen what is just technical things, technical faults actually.
Yes, but of course, in those technical issues, you also have a human factor a little bit included, obviously as well, that why wasn't this information shared properly? Why wasn't something done already before the accident? But that's how it often goes, that you need one big major accident for the legislation to change.
Mm-hmm. Well, thank you. Any questions? Yes, please. Probably not. Could you come here or just loudly say? No, here.
Sorry, I have one question. Hi.
Hey.
Regarding those hypotheses, did you make any other simulations like for other speculations, like this was some kind of
human opening, something like
human
this?
opening and some kind of explosion, just to make sure that the other hypotheses are definitely not
those flooding simulations, they were also done for different hypotheses, but not. We didn't study any collisions with other objects because it would be the study more or less the same scale as this, and so it can't be done just without really very solid plan and very solid team. But I would say for us, it shows that this all can be explained, what we see now can be explained by the laws of physics, basically. So in order to construct a sequence which is different from that, you would have to have very lot of events with extremely small probabilities lining up. So I would say, yeah, if the physics explains that, is there really, you could always construct some very strange scenarios, but we didn't do it.
Okay, thank you.
Yeah. But good question. Thank you.
Oh, thanks a lot. Yeah, sure. We have one more question, and I think we can. Yeah. So next speaker would like to ask questions.
Okay, good.
My question is, you did really impressive work. I really appreciate it. And thank you very much for sharing that with us. But my question is like that: do you really think then, with the tools which existed in 90s, it is impossible to simulate to get those findings which you got? Because let's say we have a good estimation of wave pressure on this how it visor, yes, and we have a good mechanical model for the this visor, just mechanical and final element submodels from hinge, for example. Did set, maybe that set can give already that answer already in 90s if someone would look at it?
Yes, I would say, yeah. This official investigation report in 1997, it more or less reached the same conclusions how we did. So they had, in 90s, they said already that this is the most probable cause. But of course, when the ship was designed, the tools were even less. So, and apparently the pressure values, what they use for wave loads and slamming, they were significantly underestimated. This has been proven. And the legislation for the visor locking changed a few years after Estonia was built. And while Estonia had, Estonia had 3 locks. And in those new regulations, it should have had already at least 7 locks. So it was realized quite quickly after the ship was built that there should be much larger number of locks, but this didn't apply for already built ships. But in 90s, they more or less came to the same conclusion already.
Okay, thank you very much.
Yep. Okay, thank you.
Thanks again. Yeah, I think we need to continue with next speaker. So thank you. And I will give floor to Norman Jakobsons. And Christian, could you stop your screen sharing? I'll try to run.
Can I stop it or can you stop it? Because
no, probably you need to do it somehow.
Oh my God. I don't see the option to stop sharing because there's only share option.
You can
maybe I can start sharing it.
Maybe you can just take it over from me.
Possibly, yes. Yes, should work. And this one, right?
We have to go back.
Did you manage to take over?
I think so. Hope you see our screen.
Because for me, it still shows some green. Green.
It should be our screen.
Share.
Yeah, it's shared. It's already shared.
Screen shared. They have to see it.
Okay, I think now it's your screen. Okay. Thank you. Thank you.
Thanks for your talk. And Norman,
yes,
let's start. Yeah.
Okay. Good day. My name is Norman Jakobsons. I am working from Latvia University and I am consulting sometimes about engineering and modeling. And today I am not involved anyhow in any modeling related to C or MarTe, so unfortunately. But therefore I will give more broader presentation. I will just talk about about my experience with open sourced software for modeling in some kind of real world problem situations. Maybe it's used when Vladislav invited me. That was the only thing which I can propose. So how can I get to next slide? Okay. I would like to briefly summarize approximately 20 years experience, and I will show some systems which can be modeled. And that doesn't mean I am. Then you perhaps one can do much more with OpenFOAM, but it at least can give some inspiration. Maybe that's all. I am not aiming on something very large with that presentation. First, what is OpenFOAM? I'm sorry about about my boring fast slides. Later on will be more with pictures. But when as a beginning definition, I just put some text. And OpenFOAM, it's kind of, I would like, by my words, it's a library written in C++ for numerical linear algebra, and with some kind of tensor analysis elements, and around that library is some solvers which are built around like computer fluid dynamics solver, which works as volume method. Yes. Finite volume method solvers and also finite element method solvers exist, and all this package is first was commercial. Then since 2004 it went free, went open sourced, and it can be compiled on Linux, Unix, Windows. And this code is maintained by 3 companies, generally now 3 parties. One is OpenCFD Ltd, which is holding trademark. Code is open, but trademark is not, with property. Then CFD Direct Ltd, which I think more development is on their side right now. And another branch is one of the developers for Yasak's, this branch, which is called OpenFOAM Extended. I like it the best because, let's say, when they split, it kept some new model, very interesting advanced models like diesel engine with cylinder with piston and with ignition. Everything was else with very impressive mesh morphing, and also rotating coordinates. Rotating mesh was first introduced in that version, but nowadays any of those versions can be used. What is basic traits which maybe we have to know when we start to use that? Calculations are driven by files. Basically, we have some files in directory tree, and it's almost normally no one uses graphics. Files can be modified. Solver is running. Solver is giving you some results, and if you modify those files, you can get solver react on that. And let's say if you say from that moment we will use another numerical schema for velocity discretization, then you can get next schema for velocity discretization. It will load next library, and it will work. It will continue to solve your problem. It has limited mesh generation force, block mesh, but those are really limited, and they are not really on so advanced as in commercial software. And for visualization, here is a ParaView tool, which is outside product, but also open sourced, is usually used. And generally, it can use unstructured mesh. They are one of the first, I think they are first, who used cells with arbitrary shapes. So you can use arbitrary polygons. Later on, it was incorporated in ANSYS software, for example. They took it from OpenFOAM, as much as I know. They have multi-domain. Nowadays, they have multi-domain approach, and you can have different domains with different physics in domain. We can also use multiple fields and multiple physical systems in different parts of our model. Also, it's very good for parallel scale computing. It's very well parallelized. It's scaling good on lot of on systems with more cores, and you also in systems with more nodes. Yes, because core number of cores is limited. Here is also GPU solvers, and it's more important, of course, it's easy to modify code. When I started it, it was 2005, and it was I know some my friends, I know some group in Latvian University. We did some collaborations, and they worked on crystal growth research. And they did their work for crystal growth companies in Germany. Actually, for a certain time, I think 1/3 of they consulted those companies and they did research for them. And they needed some kind of software to go forward for numerical simulations. And here it was decided that it will be open sourced, and we started with open forms at time because it was first introduced. It was recently open sourced, and it was recently, and it's looked as best as on the moment what can be. And this particular example, and then I started. It was very limited at the time, and I wrote some additional libraries and code for that. Let's say for buoyancy, I think my implementation of buoyancy is first correct implementation, because OpenFOAM itself got correctly it in, I think, 4 years later. I can be proud of that. But yes, and then yes, and the example itself is, which I'm demonstrating you, it is crystal growth example, and this by so-called floating zone model, where we have silicon beam, which is heated by electromagnetical inductor. Then it melts, and the melt is in that middle, yes, in this neck. This melt is just falling down, and here below is melted zone, and below this melted zone, crystal is starting to grow. It's growing, and this the device is pulling it down, and that was our first model. I spent almost 1 year, and it was very successful. And this is actually because here is buoyancy, here is temperature, and so on. But it's in general, it's correctly described phenomenon. Next example where it was used here in Ventspils University. I worked for some time with in Ventspils University College, and our group attention, we had some modeling group was focused on wind turbines at that time, and we did some simulations related to vertical wind turbines, as you see on the pictures. First, such a turbine was first. This possibility was to do that correctly was introduced in commercial software in 2002 in ANSYS. I would like to say fluent, but already in some 2006, I think it's even earlier. There was some division in Canadian people, guys who introduced it in this extended OpenFOAM version, which I mentioned. So everything was in place, and we started, and we did some simulations. The main idea is that we have two mesh. One is staying still, another is rotating, and they are not non-conformal mesh. In this rotating mesh, we have turbine or propeller, whatever. But since this mesh is rotating, it's rotating with all solids inside. Therefore, boundary conditions are simple. but between those meshes is another boundary which is opened and closed at every time step. And so this was already stock solver in development version, not stock. I downloaded soft code, but anyway, we compiled it and it worked. And we did try it on different blade configurations. And also here was some experimental checking of that. And finally, we got pretty well fitted curves. So that was also one successful situation. And it can be also used, such simulations can be used also in aviation and can be used in some maritime things, because related to some kind of rotating machinery which is emerged in liquid or in liquid or air. Third is my example would be maybe related to more distant things. For years I was involved in some kind of collaboration with Porsche Institute in Switzerland, and what they did spallation they used spallation targets, protons they used, which is in general it's proton beam, which hitting some kind of solid, some kind of matter, doesn't matter, solid or liquid. And neutron, and since this beam is very high, this beam is produced by high energy accelerator, and the energies of protons are very high. And as a result, with small particles, neutrons coming out, and then those neutrons, which are called spallation neutrons, can be used for different things. Let's say for material science, for neutron tomography, cancer therapy, and so on. And their usual target type was solid target, which was composed on a number of rods filled with lead. And cooled by water, which flows around them. And the proton beam is coming here and downstairs, where you see those arrows. So and neutrons are coming circularly outside, and some channels, and then they are taken from those channels. Specimens they put specimens close to this. That's the target, and the target is very safe, but not on all 100%. Sometimes some bad things happens, like you see here. Then those rods are some cracks appears on those rods. They are opening. The lead is it's molten because it's very high temperatures inside. It goes out and makes some and it's bad situation for safety. So they asked us to investigate numerically, and again we used OpenFOAM to analyze those structures. And also at that time, it was already past 2010. Here was some lot of work done even in stock OpenFOAM related to liquid-solid interaction. So we did some modeling of liquid-solid interaction related to those rods. And these models, here was some models, and this model is more work on that is done by Sabine, who she will present you, will do some OpenFOAM demonstrations later on during her PhD thesis. And also in PSI, they built some kind of experimental system, which you see here, and we did some validation. And finally, it went well. Sabine got her doctoral degree. So that's the result. More recent things. Some multi-physics simulations, which I'm doing right now. I am implementing some dynamical extensions to OpenFOAM at the moment and this is related mainly on my work in Latvia University, Institute of Physics. We are doing some kind of pumping systems, let's say basically pumps, for liquid metals. Let's say lithium, sodium. Lithium pumps can be used, for example, for production of batteries for your laptops and so on. In those factories, they use lithium pumps. Also, some of those pumps are used in so-called different branch of research and engineering for aero fusion project, which is so some of them are also just packed and given by aero fusion project. And the pump works like that. Then we have magnets here, which are connected to rotor. They are rotating, and those magnets are surrounded by pipe, which has or channel which has omega shape. And in that channel, some electrical field goes. Magnetical field induce electrical eddy currents, and electrical eddy currents interacts with that magnetical field, and finally we get some volumetrical force, and this volumetrical force be giving a pumping effect. So that is also something which is we looked at on console, we looked at on ANSYS, and all those models wasn't really what we wanted to get for the system. There was some problems with harmonics or and so on. So I just implemented it as C++ inside the additional library added to OpenFOAM, and finally, and with that small trick, that small library, I was able to simulate those pumps. I can do that. And that accuracy is more or less acceptable. You see this here, you see the productions, let's say 63 liters per second. That is typical speeds, velocities pretty much actually. And here is some kind of 2.96 is experimental result and 2.86 is calculated. So they are pretty close anyway. And the difference can be explain it because the pump is sectioned by mechanical aspects and some more additional tuning, additional code is needed in the model in order to get those currents flow through the sections. Because at the moment our model assumes those sections insulated, which is not reality. And finally, last one is something totally different. I think Monty Python had this without wording somehow. something totally different, yes. And this is related to OpenFOAM calculations, which are used in medicine, in pharmacy science, and we are modeling it right now in some project drug delivery systems. We are modeling how tablets of paracetamol, for example, how it dissolved during the time when there's some kind of flow is around it. And yes, also again, we are using extensively rotating coordinate systems and different turbulence models, large eddy simulations, time. This is not stationary, it's dynamical models. And when we are looking on results, then you can see those curves, which I think is pretty good. We can see this guy is different rotational speed for this pendulum, which you see for such a kind of machine which is mixing water, and the bottom here is tablet. And during this mixation, this tablet is dissolving. And the solution speed by this rotational speed, you see those curves here, and you see that our prediction it's kind of we cannot measure it because it is we can measure just average. Therefore, experiment is straight line, and prediction is something which you see this due to turbulence phenomenon. It's stochastic. It's not really constant, and it's pretty much in average fits the expectations. So this we do together with Riga Stradiņš University. So those are major, so few examples. I am not demonstrating here some kind of body, full over body, well, let's say, of our because I have such a simulations, but those bodies usually are some kind of unmanned airplanes or something like that, which I cannot basically show to you. Sorry, it's not my choice. I cannot legally do it, but this can be done as well. So those are just for inspiration, few examples where open form is successfully used, and it's for free. If someone says we have to pay much, no, but not really, you have to learn it. And my final notice is I would like to consider as viable alternative in some, not on all case, but on some case, the commercial solvers or package for both, and even for both, for academic or research, and for more practical, even engineering, some kind of real world engineering. This software package can be used. The strength is that we can, it's for free. We have excellent community support. Nowadays it's very simple to add new physics or more elaborate numerical models. It's easy to tailor this open form for particular problems. And as I told at the beginning, it scales well with numeric. You can get rapidly results. You can scale to numerous cores and several nodes with those cores, and HPC plus clusters, and you can do calculations of GPU. And it's for free. You don't have to pay for more CPUs, for example. The main drawbacks is then we have no advanced mesh generators. Post-processing is more or less organized well, but I would like to see better mesh generations for pre-processing. Somehow steep learning curve, and something which I didn't tell, it is constant change. Then as those open form, as all open software evolves. People coming for open software community, people going from open community, and they do change, and new versions are coming, and that is okay because things have to evolve. But unfortunately, no one almost are interested in keeping compatibility with previous versions, and it's not problem if you are just using stock solvers. But if you are doing your own code base, which in my case, I have a lot of code, then you are experiencing frustration maybe, and some problems with keeping up to date. New version can be incompatible with previous, and since it's incompatible with previous, nothing is works in new version. Okay, let's use this previous version, but for some time, after some time, this old version doesn't compile in modern Linux distribution, for example. And you are pressed to port all your code to the newer version. And sometimes it's like that, then this interface is replaced by new interface, and then they find that the new interface is not good enough and replace it back to the old. that is something which maybe is a bit more stable in commercial world. But otherwise, I would like to suggest sometimes to have a look on open source package as well. Thank you very much for attention.
Thanks a lot. And I would like to make a certificate of attendance and making the right talk in our workshop. So thanks for coming. Very much. And any questions to Normans? Maybe some questions from auditory? No raised hands. No. I have, yeah, so I actually have questions that you already answered on it. Your previous works of models like 2006, 2012, in this case, you are not able to just take it and run in newer software.
Well, I updated everything. Yeah. I am regularly updated all my libraries, and I am making my code to compatible with some software drifts. So it works on all versions practically, but it's take a lot of work to keep it in that way.
And one more question about compatibility with high performance computing and GPU. I remember from previous time it was rather challenging to run it on clusters, but how it works now in your version? Is it more clear?
This development version, which is extended version, yes, which is not really official version, but extended version, it has CUDA solvers inside. So the thing that you need proper compiler, and you can put the cards, NVIDIA, and then it will work. I am not really, I don't know how it's about AMD, this another branch, which is OpenCL, for example. That is something which I don't know.
So thanks, and so it's a good example of free software, not like a SolidWorks is costly around 12,000-15,000 per license. So it's for just like a small enterprises. I think it's very comprehensive to pay these licenses, but OpenFOAM is in this case more affordable.
Yes, sometimes yes, but of course you have to count inside your work as well. But
yes.
Okay, yes, so that's but people coming and asking to do some, yes. Okay, thank you very much.
Thank you, and we continue OpenFOAM topic, and next speaker Sabine Altner. So I need to run your presentation. Yes. Yeah, so we don't changing sharing, should be fine. You are visible for online participants as well. So, yeah.
Okay, thank you. And hello. Yes, my name is Sabine. At the moment, I work at Riga Technical University, and I will continue and keep promote OpenFOAM. Yeah, and let's start. Yes, as you already heard in the last presentation, OpenFOAM has different versions, and just for clarity, I will use for my next presentation, I will use latest version of one of OpenFOAM, which comes from OpenFOAM Foundation. Basically, OpenFOAM is developed for Linux systems, but nowadays it's also possible to run on Windows machines as well on Mac. And yeah, my demonstrations will be on Windows subsystem for Linux. If we install this on Windows machine, then we can also install OpenFOAM. And yes, and at the beginning, also, as it was mentioned previously, OpenFOAM is more or less text-based option, and there are a lot of cases, and these cases in general contains at least 3 directories. Yeah, my topic will be more technical comparing to previous. Yeah, therefore I will show you some specific things related to OpenFOAM. Yeah, and the first what we need to know is initial and boundary conditions. So we need to definite these conditions for all fields, what we would like to analyze and calculate, for example, velocity or pressure. And if we work with turbulent problems, then also parameters which are related to turbulence, like kinetic energy or something like this. Next, there is a folder constant, which contains mesh and also description of physical properties and things related to turbulence model, if we have that. And the third typical what we have is called folder system, which contains numerical settings and control our calculations. As well, for the latest versions of OpenFOAM, this contains also a dictionary for mesh generation if we use built-in functions from OpenFOAM. And yes, now I will try to show you how we can do things in OpenFOAM. And I will start with geometry and mesh. Of course, there are also options to import already created mesh in some other softwares like ANSYS, but I will show you what we can do directly from OpenFOAM. And the simplest from geometrical point of view, if we have simple geometry, which we can build from blocks or from some cylindrical objects, which we can describe as curved edge, then we can use a tool from OpenFOAM, which is called block mesh. And I will show how to do this. Yeah, so this is my screen in Windows machine where I installed this VSL on Ubuntu. And before we go to mesh, I would like to show also that we have option to get a list of available examples or tutorials. If we install OpenFOAM, then we can move to this installation folder, and there are tutorials, and you can see different categories what we can look into and try to find something what is close or very similar to our problem, and then we can copy this to our folder and do some calculations. And here I will show you a cavity example, which is very beginning. All materials which introduce OpenFOAM start with this cavity example, and it's just it's a two-dimensional problem which describe flow field or flow in rectangular geometry. And yes, as you can see here, we have these three folders which I mentioned previously. And yeah, so idea for this is that we go to system folder, then we click on this block mesh dictionary, and this is how looks our rectangular geometry. So we definite vertice. Even if I said it's two-dimensional, we need to definite for all three coordinates. And yeah. Next, we definite blocks, which is as hex here. And in this place, we can say how lot of cells we have in X and Y direction, and only one in Z direction. And it's because we would like to solve it as a two-dimensional problem. After that, we should definite all boundaries, give specific names for all of them and select corresponding type and also corresponding vertex. And here is one specific type. Front and back is defined as empty, and it actually means that this will be two-dimensional problem, and solver will not be calculating that direction any things, equations. Yeah, so this is the simplest way if we have simple geometry. And next will be example here when we have rectangular domain with cylinder, but for more complicated or realistic cases, it's good to use some parameters. And here we can see that we definite only one parameter diameter, which describe diameter of cylinder, and all other things related to geometry we definite as variables like radius or domain dimensions. Also, you can see that we are not using some constants, the same for vertex, but we use variables, and it allows us to change only one value at the beginning of this file, and we can obtain different case what to solve. And the same for layers. Also, there is used it's as a parametric way. And the same we definite blocks. In this time we need more than one, and this also is two-dimensional. We can see that we have only one cell in that direction. And for curved edge, open form has a specific option arc which allows to use curved boundary between two vertices. And next is the same, so we definite boundary, in this time inlet, outlet, and cylinder as a wall. And yeah, so this is how looks these simplest geometries. For more complicated options, there is snappy hex mesh tool, which allows us to generate mesh by snapping it to the geometry and refining it locally. And there are three steps what we can do during this snappy hex mesh tool. So we have some pre-built surface like STL file or something like this, which we can import in open form, and then using snappy hex mesh we can get the corresponding mesh. And for this I will show you motorbike example. So the same, we start with block mesh dictionary, and here we definite this computational domain, full domain, which will be as and after this computational domain, we select all things, these three steps. We can choose what we would like to do. Then we say what kind of surface mesh we will use, like here motorbike. Then we definite some refinement box, which will create smaller elements around this motorbike, and then follows list of different parameters what we can change. You see quite a lot of them, but the good thing is that there are comments which explain what each of these actually means and what we can do with these things. Yeah, I think I will not go into details, but yes, at the beginning you can just use the default values, and then if need, then go forward to check what we can improve. And here will be shown how it looks. So this is ParaView, also open source software, freely available. And this is our computational domain. And then we will take a slice, and we can see that here is our motorbike, which we imported as a surface from outer sources. And we can create some specific regions with smaller elements, and the same around these walls as well. Yeah. So this is how looks our geometry and mesh. And now I will continue with this motorbike example to show what we need to do next when we have mesh. And next we should define boundary and initial conditions. And this will be in the folder with name 0, because this is our initial calculation. And yeah, so here this will be a model which use turbulence model. Therefore, we have not only velocity u, pressure p, but also k and omega, which is related to turbulence model. And similarly, as we could generate a mesh using parameters, we can also apply similar methodology to definite boundary conditions. So here is specific separate file initial conditions, which contains all numerical values related to our conditions. Similarly, we can define boundary conditions, which will be repeated in each of these fields. Like here, for velocity, at the beginning, we say that we will use this initial condition file. We can define this, for example, fixed inlet from outer file. And yeah, next few words about this boundary condition. So fixed values from mass, it means that it's a Dirichlet boundary condition, so it's specific value for inlet or any other velocity. In this time, it's lower wall, which will move with some constant value. And no slip is applied for walls, which means that velocity on walls is 0. And in similar way, we need to define these conditions for all names what we define in our geometry and our mesh when we create it. Yeah, and next you will see the same we apply for all parameters what we will calculate, or all fields what we will calculate. This is example for kinetic energy. The same, we need to specify boundary condition and value if we have such a value. Yeah, let's move next. Now we have geometry, mesh, and boundary conditions. Next, we should say what we will solve, and this will be definite in constant folder. First of all, we see that we have some geometry here. Next, we think about momentum transport file, which specify what kind of turbulence model we will use. If we use, and in this time it's k omega SST, and turbulence on just means that we will take into account turbulence for our calculations. And we also need to specify physical properties. In this case, there is only one. It's kinetic viscosity, and viscosity model constant means that it's a Newtonian fluid. And the last things are in systems folder, and here is this tells the code how to solve. You can see there's a list of files, but most important is this control-dict. Actually, solver start with this file, and here we definite solver name. This will be incompressible fluid. We definite time interval and how often our results will be saved. As it was mentioned in previous presentation, OpenFOAM allows us to work in parallel. So in this, we can definite, for example, that we will use 6 cores or 6 processes. We can choose methods, how to divide our computational domain in 6 parts. We can also definite some additional terms, what we would like to solve, for example, force coefficient, and so on. And then in schemes, we definite how to convert partial differential equations into a system of linear equations. So here we are talking about discretization schemes. And for example, in this case, we use affine scheme, but there are, of course, several already available schemes what we can use. And the last one is solution, which dictates how to solve these large matrices, and we specify solver for each parameter what we have. And in this example, as it's steady state case, we use simple solver to calculate pressure and velocity coupling. And yeah, we can definite some other things as well here. And yes, and then the last, when we definite all things related to our case, then the last step is running our calculations. For new versions of OpenFOAM, all of these cases contains this all run script, which actually already definite step by step what we need to do. In the first time, you don't need to change here nothing, but what we can see here is that we take this geometry, then we create block mesh, then we divide in cores or do this decomposition, as snappy hex mesh typically need a lot of resources, therefore we do this there, and then hit enter, and all processes start working. And sorry, yeah, we are somewhere here. Yeah, this is how it looks when case is running. One notation that not so quickly. For demonstration, I just skip several minutes, but typically it's not so fast, especially if we are running some real life problems, then this will take hours, days, or weeks, or something like this. And therefore, it's very good if we can do these calculations on HPC cluster. And yeah, what happens when these calculations stop? Then we have all log files, which we can check. If there will be some problems, some errors, we can find here in these files. We can read and try to find what is the problem. If no, then we will obtain a result. Like this file contains all results step by step, including residuals, which is important for simulations, including some force coefficients and so on. Yeah, and as we used in this example 6 cores, then we have here for each of them available data. And also we can get in other formats output data for post-processing as well. And the last is our results for the last time step. As this is a steady state case, then we are not interested in all time steps, but just the last one. And as you saw here, it looks very strange, but it's because format is binary. It's take less memory, but we could save these results also in ASCII format, and it allows us to read these data from each of these files. And the last or one additional post-processing option is to create VTK files, which allows us to look on obtained results in graphical way, and this will be shown here. The same open form, and we should find this VTK file which we created, then click on apply, and then we can do analysis of our results. Here I will show only a very simple case that I take the same slice and I look on flow field around this motorbike. But there are more options. We can create vectors around some objects. We can apply some thresholds or a lot of different other things that we can do here. And I guess that's all from my side. Here are a few points, but yeah, I think I can stop here. So thank you.
Thanks a lot. An old school total commander or midnight commander and binary files and text files. But finally, anyway, you get a visual results, and you can just cut it in slices and rotate maybe and just use visual results, not data. But finally, anyway, use numerical data, like the numbers, to analyze it.
Yeah, we can do both. We can look on these graphical things using, I don't know, Python or something like this. We can create graphs, and we can look also on these fields using ParaView, and this allows us to get more complicated analysis for analyzed problem, I guess.
Yeah, thank you. So, any activity in Zoom? No. Thank you for inviting the talk, and nice to see you back to Ventspils. Yeah. Okay. Yeah, so we will continue with our next speaker, Marina Konjuhova. I hope Marina are you here?
Yes, I will try to share my presentation.
Could you be a bit louder?
Yes, I will try to be more louder. Okay.
Okay, we see your screen.
Okay.
And yeah, so let's start. So Marina Konjuhova, another way of modeling data, like using console. Yeah, so floor is yours. I switch my camera and switch my microphone not to disturb you.
Thank you, Vladislav. Hello, everyone, and thank you for the invitation. My name is Marina, and I work at Places at Institute of
Marina, maybe a bit louder, so I don't know why, but your voice is not so clear.
Now, do you hear me?
I hear Marina.
I try and provide a good talk.
Okay, yes, I think it's okay, yes, sorry.
So I'm from the Institute of Solid State Physics and Ventspils International Radio Astronomy Center at Ventspils University of Applied Science. And today I will present our work on the numerical modeling of hydrogen compression using the liquid piston concept. This study is based on multiphysics simulations performed in COMSOL multiphysics. As all you know, hydrogen is one of the most abundant elements on Earth, and it's widely seen as a key energy carrier for the clean energy transition. And it's especially important for sectors that are difficult to electrify. For example, heavy industry, long-distance transport, and maritime applications. Hydrogen also enables energy storage from renewable sources like wind or solar power, helping to balance their intermittent nature. For this reason, hydrogen is strongly aligned with the European Union's goal of achieving climate neutrality by 2050. And it's expected to play a significant role in future marine and maritime energy systems. However, the use of hydrogen at sea comes with specific challenges, particularly in terms of storage and compression, which require safe, efficient, and cost-reliable compression technologies. On this figure, you can see a typical hydrogen compression infrastructure from production to high pressure storage. And hydrogen can either be delivered to the site or produced also locally using electrolysis and often powered by renewable energy sources as wind or solar. And in this case, we usually refer to green hydrogen, which does not produce CO2 during production. After production, hydrogen needs to be compressed from low or medium pressures to the high pressure levels and required for storage and distribution. This compression stage is key part of the overall infrastructure. In marine and maritime systems, the same concept applies, but of course, additional requirements appear. Equipment needs to be compact, reliable, and suitable for offshore conditions. This slide shows the concept of a hydraulic hydrogen compression system based on the liquid piston principle. This compression concept has been developed by our research group at Ventspils University of Applied Sciences and is protected by several national and European patents. In this system, hydrogen is compressed in several stages using a hydraulic working fluid. In our case, it is silicone oil, which acts as a liquid piston. The use of liquid piston allows smooth and well-controlled compression. The system includes primary and secondary compression stages, high pressure storage, and set of valves that control both gas and fluid flow. One of the main advantages of this approach is a relatively small number of moving parts. Also low noise levels and improved thermal management. And in general, this system can reach pressure of up to 100 megapascals. That making it suitable for port infrastructure and offshore platforms. This slide summarizes conventional mechanical hydrogen compression technologies such as reciprocating piston, linear, and diaphragm compressors. And all these technologies are well established and widely used in stationary and automotive applications. They can achieve high compression pressures and have proven performance. However, when we move to marine and offshore environments, some of their limitations become more pronounced. Mechanical compressors typically involve many moving parts, which leads to higher maintenance requirements as well as increased vibration and noise. And as a result, conventional mechanical compressors are not always, let's say, the optimal solution for marine hydrogen infrastructure. And this motivates the search for alternative compression concepts that can offer a little bit simpler design. Here you can see the alternative solution. And in this liquid piston concept, in this approach, hydrogen is compressed by a liquid column that acts as a piston inside a fixed volume chamber. And this allows the compression process to be smooth and also well controlled, while avoiding many of the mechanical issues found in conventional compressors. An important feature of the liquid piston is its thermal behavior. The liquid absorbed heat generated during the compression and can be cooled more effectively. And as a result, the overall compression efficiency can increase from typical value of 17% to over than 85%. To better understand how hydrogen behaves during compression process, we use numerical modeling. This allows us to study how pressure and temperature change during the compression process and to design a more safer and more efficient system. One of the main advantages of simulation is that the different operating conditions can be tested without physical experiments. We can change compression speed, geometry of the chamber, or working for fluid, which saves the time and cost and helps improve system performance. Here you can see the model. It has height of 145 millimeters and a diameter of 100 millimeters and the total volume of a little bit more than 1 liter. Hydrogen is located in the upper part of the chamber, while oil acts as a working fluid below. As the oil rises, the hydrogen is compressed. The simulation includes heat transfer between the hydrogen, the oil, chamber walls, and the surrounding environment. And this multi-physics approach allows us to analyze temperature variation, heat losses, and pressure development during the compression cycle. Here you can see liquid piston compression chamber that was implemented in console software. We used, as I talked previously, a multi-physics approach that combines compressible gas flow for hydrogen, incompressible flow for the liquid piston, and unsteady heat transfer. The model includes all the main parts of the system: the hydrogen region, the liquid piston, and of course steel chamber walls. During compression, the gas and liquid are compressed together, and heat transfer between the hydrogen working fluid and the chamber also is taken into account. This allows us to analyze how pressure and temperature change during the compression cycle. In console, implementation begins with model parameterization. All key parameters are defined in the global definitions section. This includes key geometric values such as piston stroke, cross-section area, and compression chamber height, as well as initial conditions. Defining these values as global parameters mean that the same values are used consistently throughout the model in geometry, in physics interfaces, and study signals. The next one slide shows that we set the initial conditions using global variables. This includes the initial pressure, the initial gas, volume, the mass of hydrogen, in the compression chamber and also compression time. The key point here is that the gas volume and density are described by time-dependent expressions. This allows us to represent the compression process continuously rather than a series of discrete steps. And in this way, the thermodynamic behavior of hydrogen is directly related to the geometry and motion of the fluid. In the next step, we determine environmental conditions, such as temperature and pressure. This allows us to account for heat exchange between the chamber walls and the surrounding environment. This allows the model to include realistic heat losses, which is important when analyzing temperature change during a hydrogen compression process. Model geometry. Here you can see the geometry of our model. We use a 2D axisymmetric model, which is well suited for this type of cylindrical system. The chamber is divided into three regions: hydrogen domain, still chamber, and liquid piston. And this configuration is sufficient for realistically studying compression and heat transfer effects. Besides building the model directly in console software, the geometry can also be imported, for example, from the SolidWorks. This slide shows how material properties are defined in console model. Material parameters are defined for all regions. We define key physical properties such as thermal conductivity, heat capacity, viscosity, and density, which directly affect both heat transfer and fluid flow during compression. And these properties are used consistently across all associated physical interfaces. You can use materials already available in console software, or also it's possible to enter them manually. This slide shows the physical properties of the material used in the model. For hydrogen, we use standard thermodynamic properties such as molar mass, heat capacity, and heat capacity ratio. These parameters are necessary to describe the change in temperature and pressure during compression. The liquid piston is characterized by thermal conductivity, density, viscosity, and heat capacity. This slide shows how chamber geometry and piston motion are implemented in console. The fluid piston motion is achieved by moving the boundaries using the deformed geometry feature, rather than moving the entire mesh. This approach allows for smooth changes in gas volume during compression, while maintaining mesh stability and avoiding mesh rebuilding at each time step. And as a result, we can accurately track the compression process with good numerical stability and reasonable computational costs. Okay, this slide shows how heat transfer is considered in the console model. For all major parts of the system, hydrogen gas, liquid piston, and chamber walls, during the compression, heat is generated in the gas and partially absorbed by our liquid piston. In the model, volumetric heat sources are defined within the liquid regions, and appropriate thermal boundary conditions are applied to the chamber walls. And this allows for the description of both heat generation within the system and heat loss to the environment. With this setup, console solves the coupled problem of fluid flow and heat transfer. In COMSOL, hydrogen is described as a creeping and compressible flow. Due to these low velocities, inertial effects can be neglected without loss of accuracy. At the same time, the compressibility of the gas is fully preserved. Since pressure change during compression are the key physical effects we want to account for. The isosymmetric formulation further simplifies the problem while maintaining the correct flow physics. And taken together, this approach provides a stable and physically consistent description of hydrogen behavior during the compression stroke. The motion of a liquid piston is implemented in the COMSOL model in the next way. The liquid piston is not modeled as a mechanical component that I have already mentioned, but this component moving inside and stick its motion is driven through a moving boundary at a specific velocity. This boundary represents the interface between the liquid and gas and moves upward during compression. And as a result, the gas volume continuously decreases, making the compression process controllable and physically consistent. A significant advantage of this approach is its numerical stability. Since the mesh itself does not move or deform significantly, remeshing is not required during the compression cycle. Here you can see the mesh in the COMSOL. The finite element mesh is generated for the entire computational domain, including the hydrogen region, the liquid piston, and the chamber walls. To ensure sufficient accuracy, the mesh is locally refined near the solid-liquid interface, as this is where strong velocity and temperature gradients are expected. Specifically, boundary layers elements are applied along all chamber walls and in the region of the moving liquid piston. This mesh design allows for the correct consideration of both flow and heat transfer effects without excessively increasing the overall number of elements. And as a result, this achieves a good balance between numerical accuracy and computational efficiency for simulating transient compression. The model uses a triangular finite element mesh. In the hydrogen region, the mesh is relatively coarse, as the flow is smooth and the velocity are low. But at the same time, the mesh is locally refined near the interfaces between the hydrogen, the liquid piston, and the steel walls. These regions are crucial for resolving heat transfer and boundary effects, so boundary layers elements are used there. As the liquid piston moves upward, the hydrogen volume decreases step by step. The mesh smoothly deforms with this movement, following the change in gas volume without restructuring. And in total, the mesh contains approximately 21,000 elements, providing a good compromise between numerical accuracy and computational cost for unsteady state simulation. We used a time-dependent study. The simulation time corresponds to the specified compression duration, and in our model, the longest compression was 20 seconds, and the faster 0.5 seconds. All physical processes are solved in a fully coupled way. This includes the flow of compressed hydrogen, the movement of liquid piston through the deformed geometry, and heat transfer in gas, liquid, and chamber walls. This model allows us to track continuous change in pressure and temperature during the compression process. After running the model, we obtain results and can review and analyze obtained data at each calculation step. The average temperature is calculated separately for each region. The hydrogen gas, the liquid piston, and the steel walls of the chamber. This allows us to clearly separate the thermal behavior. By examining average values rather than local peaks, we can trace general heating trends during the compression process. This analysis is particularly useful for understanding the role of liquid piston as a thermal buffer and for assessing the efficiency of heat transfer to the chamber walls. And this information also is important for optimizing the compression rate and geometry of the chamber. Once the calculations are completed, we can calculate the average temperature in each domain. You can see the temperature, for example, at 5, 10, and 20 seconds. We can see also the average temperature results for any time period. This slide shows the temperature distribution inside the compression chamber at different points of time. On this slide, the results are presented for 3 characteristic times, 3, 10, and 20 seconds. During the early stages of compression, the temperature increase in primarily concentrated in the hydrogen region as the gas is compressed by the liquid piston. As the process continues, heat is gradually transferred to the liquid piston and then to the steel walls of the chamber. And this becomes more notable after 10 and 20 seconds. And also these graphs clearly illustrate the transient thermal behavior of the system and show how the liquid piston and chamber walls contribute to the redistribution and removal of heat during the compression. Thus, the process occurring during a single compression stroke was simulated using the presented model with compression stroke time varying from 0.5 to 20 seconds. The initial hydrogen and oil temperatures were set at 300 Kelvin, and the compression ratio was equal to 5. The calculation results for 2 scenarios are shown here, and one with an initial gas pressure 3 megapascals and another one with 20 megapascals. Figure 16 shows the temperature field distribution within the cylindrical chamber. The figure shows the evaluation of the gas temperature over a 20 seconds stroke at time interval 0, 10, 15, and 20 seconds. And these results highlight the significant heating effect within the gas as compression progresses, especially at high pressure. Figure 15 shows the temperature change over time during a single compression stroke for hydrogen, for working fluid, and chamber walls at initial pressure of 20 megapascals and compression ratio 5. That's not a lot of time, maybe about results. The results of the compression process simulation allow us to estimate the temperature increase of the gas and the working fluid, in our case is liquid oil, and therefore determine the energy expended during the compression process. On these figures, you can see how the average hydrogen temperature and oil temperature changed during one compression stroke depending on the initial pressure in case of 20 and 20, 15, 10, and 3 megapascals. Here you can see the temperature increase predetermined in the model corresponds to the energy expended in the hydraulic compression process of hydrogen and stored in the hydrogen, oil, and cylinder body in walls. The amount of energy stored in the compressed hydrogen, oil, and steel is determined using an equation based on the laws of thermodynamics. Here you can see energy distribution at initial pressure of 3 and 20 megapascals. And this diagram shows that most of the energy is concentrated in hydrogen during the compression. But of course, under real conditions, hydrogen and oil mix and exchange heat. When mixed, the gas cools and the oil heats up, resulting in a more balanced overall temperature regime within the chamber. This slide shows temperature change for varying compression stroke duration at initial pressures 3, 10, 15, and 20. The next one slide, it shows the relationship between the power required for compression and the duration of the compression stroke for 4 different initial pressures. Figure 24 shows the increase in hydrogen temperature at different compression chamber heights. We have changed height of the chamber. The results here clearly illustrate how chamber geometry and compression duration affect the thermal behavior of hydrogen during the compression. On these figures, you can see that the chamber size has a significant effect on temperature change at low volume, but eventually stabilized. And these trends suggest that while large chamber volume contribute to greater heat release, their effect diminishes at higher volumes, indicating an upper temperature limit beyond which increasing volume has little effect on temperature increase. Maybe I will skip this because it will be in conclusion. And conclusions. In conclusion, it should be noted that numerical results demonstrate that liquid piston compression provide effective thermal management during hydrogen compression process. And chamber geometry significantly influence both temperature and energy consumption, making the optimization necessary. Due to their compact design and favorable thermal characteristics, liquid piston hydrogen compressors are well suited for use in the marine and offshore hydrogen industry. So thank you for attention. Are there any questions?
Thanks a lot. Any questions, comments? Yes, we have questions from Norman Jacobson. Norman, could you come, please?
Excuse me, did I get correct? So then your compression cycle is about 20 seconds. Is it like that?
We can change. We can start from 0.5 until 20. Yes, but on this result, you saw that we compare how this compression time depend on pressure.
Okay, half a second is faster and 20 is slower. I'm just wondering about and how high, what is height of your, how long it is your cylinder?
145 millimeters. It's very small, 1 liter.
So this velocity is well below 1 meter per second in any case, average. So, but then my question is, you are using boundary finite elements. Boundary finite elements is usually used for boundary layer to reveal boundary layers, as physicist Frankl introduced them in the previous century, beginning of previous century. And do you think this is really needed to use boundary layer elements in the case when your velocities are so low? Because this can be avoided.
It's a discussable questions, and because we have no mixing between our domains. Yes, it's separately hydrogen and liquid piston. And maybe I needed more that when we develop this model, our local Latvian Process Analysis and Research Center helped to us to create this model, because it's very tricky in this in total to model a compression process. And they decided, they help us to create, and they help with meshing, and they offer.
Okay, that was their idea, to put boundary elements on the NEARS walls.
I will obviously fix this, and maybe we are planning to continue our modeling, so maybe we will something to change and prove our model.
Yes, I would like to suggest to do the same modeling without boundary elements and check what is the difference. I don't know, maybe it has something else which I missing, which I didn't see at the moment now, but my suggestion is to try without them and see, did you have different solution? Thank you very much.
Thank you very much. Yes, we will use your recommendations.
Thank you. Thank you, Norman, for comments. Yeah, actually, in this case, we have different kind of speeds, because minimum speed is 0.1 second. So and the compression speed would be several, even 10 meters per second, even more. But yeah, so we will try to investigate this as well. Thanks, Marina. Any other questions? No. Yes, thank you for all listeners and participants and speakers as well. So now we have a coffee break, and we relocate to another, not building, the same building, but another block A, for computer class, and we'll try to run SolidWorks and see how it works in reality. And who willing to attend from remote site, just stay in same Zoom, we reconnected from in our computer and join ourselves and continue discussions from another room. Yeah, again, so thank you, and we will have 15 minutes, maybe, let's say 10-15 minutes break now.
Recording stopped.